All right, this is question number 3 from the 1999 AP Calculus AB exam. This is a rate FRQ, and we're given a chart at which water flows out of a pipe, given in gallons per hour. It's a differentiable function R, and we have the measurements every 3 hours for a 24-hour period. Part A just asks us to use a midpoint Riemann sum with 4 sub-intervals of equal length to approximate the integral from 0 to 24, and then explain the meaning. So we'll do the integral first, right? From 0 to 24, 4 subdivisions of equal length from 0 to 24 will be 0 to 6, 6 to 12, 12 to 18, and 18 to 24. If we're looking for the midpoints of each of those will occur at 3, 9, 15, and 21. And so first off, we have to take the length of the interval, which is going to be 6 for each of them. And then we just want to multiply that by the values of R at 3, 9, 15, and 21, which are 10.4, 11.2, 11.3, and 10.2. Now, this is a calculator question, even though it's number 3, because back in 1999, the first 3 were all calculator questions. So you could use a calculator to total all that up if you want. 0.2, 0.2, 0.4, and 0.3 is 1.1. And so if I add 10, 11, 11, and 10, we're going to get 42 plus 1.1 is going to be 43.1. And 6 times 43.1 should come out to be 258.6 gallons. And what this means, since we've integrated a rate, it's the total amount of whatever this rate is about, which is water flowing out of a pipe. So the integral from 0 to 24 of R of t is the total gallons of water. And in fact, it asks the meaning of our answer, which isn't the integral. So what we'll do, instead of writing this integral is the total amount, we'll say that 258.6 is, and not just the total amount, but we'll say an approximation or an estimate of, we'll be specific and actually do what they're asking, talk about what our answer means. It's an estimate of the total gallons of water that flow out of the pipe and we'll say during the 24-hour period. And they'll give you 3 points here for this. 1 for the appropriate setup of the Riemann sum, 1 for the value, and 1 for your explanation. In part B, it asks us, is there a time when R prime is equal to 0? And so R prime can equal 0 whenever the average rate of change is equal to 0, as long as the function is continuous and differentiable. If R is differentiable, that guarantees it is continuous. So we can say R is differentiable, and we'll say on 0 to 24, so continuous on 0 to 24. And of course, we want brackets on our continuous part because that's the conditions of the mean value theorem. So it's continuous on 0 to 24. So the mean value theorem applies. We want to make sure we state the mean value theorem. And then we'll say the average rate of change from 0 to 24, right? So F, or we'll say R of 24 minus R of 0 over 24 minus 0 is equal to r of 24 is 9.6, and r of 0 is also 9.6. And so this is equal to 0. So r prime of t equals 0 for some t on, and we'll say the interval 0 to 24. That's what the mean value theorem says, right? It says if the average rate of change equals something, in this case 0, then the instantaneous rate of change of it, so the derivative of r, must also equal 0 on that interval. Must equal that same number. And they're going to give you 2 points for that. One for yes, it does, and one for the explanation of mean value theorem, and that it's continuous and differentiable and all that good stuff. And here in part C, it says the rate of water flow can be approximated by Q of t, which is this other function, 1/79th of 768 plus 23t plus or minus t squared. And use that to approximate the average rate of flow of the water during the 24-hour time period. Well, the average of Q, right, should just be 1 over, this is the mean value theorem for integrals, 1 over 24 minus 0 times the integral from 0 to 24 of Q of t dt. And of course, since this is a calculator question, we can just use our calculator to approximate what that is. Right? And so we'll go into our calculator. I'm going to hit alpha x to give me a nice little fraction. Just put 1 over 24 out in front. And my integral will come from hitting math. And option number 9, we're going to integrate from 0 to 24 of our function q of t. Well, q of t was 1 over 79 times that little polynomial we had there, which was 768 plus 23t, we'll use 23x, minus t squared, so we use x squared. We'll close off our parenthesis for the little polynomial. We'll go over here and say dx, and we get 10.785 gallons per hour. And it's going to be gallons per hour because it's the average rate of water flow. Well, the rate of water flow is going to be in gallons per hour, as we were told earlier in the problem, right? When we had this setup of the units. It's right up here, right? Gallons per hour is how this is all measured. And so that was worth, let's see, that was worth 3 points. 1 for having the 1 over 24 minus 0 and an integral from 0 to 24. 1 for it being q of t inside, and 1 for the final answer. And then you also got a point for the units in both A and part C. That was worth 1 final point to give you all 9 points for this rate FRQ. Question number 3 from the 1999 AP Calculus AB exam. All right, this is question number 4 from the 2000 AP Calculus AB exam. This is a rate FRQ. We got water pumped into an underground tank at a constant rate of 8 gallons per minute and water leaking out at root t plus 1 gallons per minute, all from 0 to 120 minutes. And at the beginning, at t equals 0, the tank has 30 gallons of water. We want to know how many gallons of water leak out from t equals 0 to t equals 3. Well, in order to figure out an amount that leaks, we have to integrate the rate at which it leaks on that interval. So we'll just do an integral from 0 to 3 of root t plus 1 dt. And of course, this is a basic u sub. We'll write it out if we want here. It's u equals t plus 1, where du is just the derivative of that, or dt. So I can rewrite this as an integral of root u, or u to the 1/2 du. And instead of 0 and 3 now, since if t equals 0, then u is going to be 1. And if t equals 3, then u is going to be 4, just by plugging those into u equals t plus 1. So we're now going to integrate from 1 to 4. And when we do that, and of course you don't have to do the u substitution. If you want to do the integral in your head, you don't have to write it out, and that's fine. The integral of u to the 1/2 is just 2/3 u to the 3/2, and we'll evaluate from 1 to 4. And so when we do that, we've got 2/3 of 4 to the 3/2 minus 1 to the 3/2, which is going to be 2/3 of 4 to the 3/2. First you square root the 4 to get 2, and then cube it to get 8. And 1 to the 3/2 is just 1. So we end up with 14/3. It doesn't ask for units, it asks us how many gallons, so it's pretty obvious that this is a gallons value. We got 3 points for that. 1 for the setup with the limits, 1 for the correct integrand, and 1 in the end for our final answer. In part B, it asks us how many gallons of water are in the tank at t equals 3 minutes. Well, we just found how much water leaks out in those 30 minutes. So we then need to figure out how much water is pumped into it in 3 minutes. Well, if it's doing 8 gallons a minute, right, pumped in is just going to be 8 times 3, which is 24. So the total in the tank should be the amount we started with of 30 plus the amount pumped in of 24 minus the amount that was removed of 14/3. Well, 30 and 24 is 54. 54 is 162/3. So we have 162/3 minus 14/3, which is just going to give us 148/3. And again, it's already given us the units of gallons, so that's perfectly sufficient. And we get 1 point for that answer. In part C, it says write an expression A of t for the total number of gallons of water in the tank at t equals, at any given time t. And so what we really want to do here is just, think about our function here, A of t, right? A of t is the amount in the tank. So we know that we started with 30. So whatever we do is going to be 30. And then plus, we're going to have the amount that is pumped in, which is just going to be 8 gallons times the number of minutes, 8t. And then we have to subtract the amount that leaks out, right, which is an integral from 0 to t of that square root function, right? Square root of x plus 1 dx. And this would be a perfectly acceptable answer here for part C. And they would give you 2 points for this, 1 for this, and 1 for this. And of course, if you had an 8 minus the root x plus 1 inside the integral, that would also be perfectly acceptable and earn you all 3 points. In part D, it says, at what time is the amount of water in the tank at a maximum? Well, we already know what the amount of water in the tank is. The amount of water in the tank, A, is equal to the function we just had, 30 plus 8t minus the integral from 0 to t of root x plus 1 dx. Well, to figure out when a function is at its maximum or minimum, we take its derivative, right? A prime of t is just equal to 8, because the 30 goes away and the derivative of 8t is 8, and then a minus, and the derivative of an integral from a constant to a variable of the function there is just the function in terms of t, in terms of that top variable. So we want to know when, first of all, does this equal 0? Right? That's the only possibility of when we could have a max or a min. Well, just solve for t, right? We'll get 8 equals root t plus 1, square both sides. 64 is t plus 1, or t is 63. So our derivative equals 0 at 63. So that could be a max, or it could be a min, dependent on the values at 0 and 120. So you could evaluate the amount function at 63 and at 0 and at 120 and see which one is the biggest. Or, better yet, we could just see if our derivative is positive or negative to the left and right of 63, since we only have one critical value for our derivative on that interval. So I think that'll be easiest. We'll just make a sign chart for A prime, putting 0, 63, and 120 on it. And if I pick something less than 63, like 1, and put it into my A prime here, I get 8 minus the square root of 2. Well, 8 minus the square root of 2 is certainly a positive number, which means A is increasing. And if I put in something more than 63, let's say we put in 99, just because that's easy to evaluate here. 99 plus 100, or 99 plus 1 is 100. When we square it 100, we get 10, so 8 minus 10 is a negative. So if A prime is positive on 0 to 63, and then negative for 63 to 120, that means A must have its maximum at 63. So we'll say, since A prime greater than 0 on, and we'll say from 0 to 63, and A prime less than 0 on 63 to 120, A has a maximum at t equals 63. And you get 3 points for that. 1 for just setting A prime equal to 0, 1 for solving for 63, and 1 for the justification. Don't just draw the sign chart, actually write out the statement that A prime is positive, then A prime is negative, and the change occurs at 63. And that is the end of this rate FRQ question number 4 from the 2000 AP Calculus AB exam. All right, this is question number 2 from the 2002 AP Calculus AB exam. This is a rate FRQ, and we've got a rate at which people enter an amusement park, that's E of t, and we've got a rate at which people leave the amusement park, that's L of t, and t is measured in hours after midnight, and the functions are valid from 9 to 23, which is the hours during which the park is open. And it says at t equals 9, there's nobody in the park. So we want to know how many people have entered the park by 5 p.m. or at t equals 17. So in order to figure out the actual amount of people, we need to integrate the rate that they enter, right? We want the number of people that have entered. So we want to integrate the rate at which they have entered. So we're going to integrate from t equals 9, the beginning of our function when the park opens, till 5 p.m., which they've told us is t equals 17, of the function e of t dt. This is a calculator question, which is great because otherwise that's kind of an annoying function for us to try to integrate. So we'll go to our graphing calculator here. And what we'll do is we're just going to go to math, and then we're going to go down to option number 9, which says FNINT. We'll hit enter there. We're going to integrate from 9 to 17, and we're just going to type in our e of t function, which you can hit alpha x to get this nice fraction if your calculator does it. And we can have 15,600 divided by t squared. So we'll do x squared minus 24x plus 160. And I forgot to hit the dx out at the end, so we'll put our dx out at the end, and now it will tell us that it's 6,004.270. And it says to the nearest whole number, so we will say 6,004 people enter during that time interval. They gave you 3 points for that. 1 point for having the correct limits from 9 to 17, 1 for having e of t inside, and 1 for the final answer. In part B, it says the price of admission to the park is $15 until 5 p.m. And after that, they drop the price to $11. And so we want to know how much money, how many dollars are collected from admissions to the park on the day. And so, well, all we're going to do is we're going to integrate e of t, again from 9 to 17, and multiply that by, we'll multiply that by 15 because that's how much it costs to get into the park on that time interval. And then we'll add to that 11, the cost for the rest of the day, times the integral from 17 to the end of the park being open at 23, again, of e of t. And we'll just have our calculator figure out what that is. So we'll go back to our graphing calculator. Now, we already did this integral, so I'm just going to go back up. Actually, what I'll do is I'll just type 15, and then I'll go back up here and hit this integral. So I have 15 times that integral now. And then I'm going to say plus 11, and I'm going to go back up and just do that again. But I don't want 9 to 17. Now I want my lower limit to be 17. And I want my upper limit to be 23. And so I can just go ahead and I don't have to retype the whole function every time. I can just go back up, highlight the one thing and change it. When we hit enter, we get, looks like 104,048.1652, which will approximate to the nearest dollar as 104,048 dollars. And they gave you just 1 point for having the correct setup there with the answer. In part C, they said, let h of t be an integral from 9 to t of e minus L on 9 to 23. And it tells us that the value of h of 17 to the nearest whole number is 3,725. And they want us to find the value of h prime of 17 and then explain what the meaning of it is in context of the amusement park. And so of both h of 17 and h prime of 17. So first of all, let's find this value of h prime of 17. Well, h prime of t, well, that's just an integral of a derivative, a derivative of an integral from a constant to t of some function. So it's just that function in terms of t. So h prime of 17 is just equal to e of 17 minus L of 17. And so we can just evaluate each of those functions at 17 and subtract them. And they want this, let's see, they didn't tell us to round this or anything. So we'll see what we get on our calculator. E of 17 is just going to be the original function at 17. So that's alpha and x to get us a nice fraction, 15,600 over, well, now instead of typing x squared, we're just going to do 17 squared minus 24 times 17 plus 160. And then we will we'll subtract from that L of 17, and L was also a fraction, so we'll do alpha x to get the little fraction for L. And L was 9,890 over t squared, so we'll do 17 squared, minus 38t, so we'll do 38 times 17, and then plus 370. And it looks like that comes out to be, and it's given us a fraction here. So I guess that's a perfectly acceptable fraction as an answer, but I want to see what that is as a decimal. So I'm going to hit math and go down to option number 2 and get the decimal of negative 380.281. So this is negative 380.281. 281, yep. And now it wants us to explain the meaning of h of 17 and h prime of 17. Well, h of 17, and h of 17, well, that's the amount of people that entered minus the amount of people that have left, right? Because we integrated E minus L from 9 to 17 to get that value. And so that's just the total number of people in the park at t equals 17. So we'll say it's the number of people in the park. And it says in the context of the problem, so we won't say t equals 17. We will say at 5 p.m. because that's what t equals 17 was, right? At 5 p.m. So h of 17 is the number of people in the park at 5 p.m. And then the second part, what does h prime of 17 mean? Well, that's going to be, it's the rate of change of the people in the park. So if it's negative, we're going to say h prime of 17 means the number of people in the park is, since it's negative, decreasing at, and then it's negative at 300, we'll say, 380 people per hour at 5 o'clock p.m. And they gave you 3 points for this. They gave you 1 point for just getting this value here and 1 point for each of the explanations. And here in part D, it says, at what time from 9 to 23 does the model predict that the number of people in the park is a maximum? And so, well, what we need to have here to figure out when we have a maximum is when the rate of change is equal to 0, right? When the E minus L, or in other words, when h prime, right? If h prime of t, which is E of t, minus L of t is equal to 0, that's when we could have a potential maximum or minimum, or on the 9 to 23 interval, since it's closed, it could be at 9 or at 23. Now, it's obviously not going to be at 9 when the number of people in the park was 0, but we can see when E of t minus L of t is equal to 0 by just going back to our graphing calculator, hitting y equals, and we'll put in the function E of t minus L of t. So just going to retype E of t minus L of t here, and then graph it and see when it's equal to 0. So that'll take me a second here, 9,890 over x squared minus 38x plus 370. And we're talking about the interval from 9 to 23. So I'm going to hit window and pick my x minimum to be 9 and my x maximum to be 23. And when I hit graph now, we can see not very much of our graph, which isn't super helpful. But what we can do is we can hit zoom, and we can go all the way down to option 0 here, zoom fit, and it should fit everything on our graph there, so we can see what's actually happening from 9 to 23. And this is the graph of the derivative of h. Well, it's positive all the way up till we get to this x-intercept here, and then it's negative all the way after, which means that the function is increasing. H, the number of people, is increasing, and then at this point, it starts decreasing, and it never starts increasing again because that derivative is always negative all the way along here after that. And so our maximum must be at that x-intercept, so we'll hit second trace. Option number 2, 0, and we will calculate that value. We'll go to the left and hit enter. We'll go to the right of the intercept and hit enter. We'll hit enter once more and see that we get at 15.795. And so what we'll do is we'll say at t equals 15.795, and we know it is a max because h prime of t changes from positive to negative at that point. And therefore, H is going to go from increasing to decreasing. So the number of people in the park is increasing till then and then decreasing after that. And they gave you 2 points for that. 1 for just setting E of t minus L of t equal to 0, and 1 for the correct answer with that explanation. And that is the end here of this rate FRQ question number 2 from the 2002 AP Calculus AB exam. All right, this is question number 5 from the 2002 AP Calculus AB exam. I'm calling this one a rate FRQ. It's not our traditional rate FRQ. In fact, it's even in the non-calculator section here. It's more of a related rate one, which they've kind of gone away from, but you never know what they might decide to bring back any given year. So we're given a cone here that's got some water in it, and the water is evaporating. So that H is changing at -0.3 of a centimeter per hour. And we know the height of the entire container is 10. And we know that the diameter of the opening at the top is also 10. And we want to find the volume of water in the container when H is equal to 5. Well, this should be fairly straightforward. We know that the volume of a cone, which they did not, oh no, they did give us it, is 1/3 pi r squared H. So we want to find the volume when H is 5. Well, that's going to be 1/3 of pi times our radius squared. Well, we'll have to figure out what that is in a second, and then times H of 5. Well, we should be able to see that this is really just, some, if I were to like draw some little lines in here, right? What we're really getting here is, as this water level decreases, we've got some similar triangles that can be made by taking the center of that circle that represents the base of the cone, dropping it down to the vertex of the cone, and then going straight over to the side here, and then using the edge of the cone. We get a couple of similar right triangles here. We know they're similar because those are both right angles, because they are, it's a right circular cone, and they share this angle in common. And so the ratio of the radius across the top, which is 5, to the height there, which is 10, should be equal to the ratio of our r here to our h going up and down, right? This h right here for the smaller right triangle. And so if we're looking for what r is here, well, r is equal to 1/2 h if we just multiply both sides by h. And that's what we're looking for, is what is r, because we need to put in our r squared there. Well, if h is 5, then r is 5/2. So we'll put in 5/2 here. And when we multiply all of this out, in the numerator, we got a 1 times a pi times 5 times 5 times 5. So we're going to have 125 pi. And the denominator, we just have a 3 times 2 squared, which is 12. It says indicate units of measure. So these are just going to be centimeters cubed, right? Since we know that the height and the radius are in terms of centimeters. So this is a volume, it'll be centimeters cubed. You just get 1 point here for doing that. Then in part B, it asks us to find the rate of change or the volume of the water in the container with respect to time when H is 5. So it would be probably easiest for us to just put everything in terms of H. Right? So if we go back here, we already know that R is 1/2 of H. So if I look at my formula for volume, which was 1/3 pi times r squared times h, I'm just going to put in 1/2 h for my r to give me a volume formula that now in my numerator I've got a pi, and I've got an h squared from the parentheses plus another h. That's going to be pi h cubed, and it's all going to be over 12, right? Because we have 2 squared and a 3 in the denominator. So now, when I take the derivative of this with respect to time, I will get dv dt, which is what we're looking for, the rate of change of the volume of the water, is equal to the derivative of pi h cubed over 12. Well, multiply by the 3, that's going to give you 3/12, right, or 1/4 the pi h squared when we drop that by 1 degree, since we're taking a derivative of it, and then a dh dt because we're taking the derivative of an h term with respect to t. And, we know what dh dt is. It was given to us initially. We know what h is here, so all we really have to do is plug in our values, right? We're going to get 1/4 of pi times h, which is 5 squared, times dh dt, which is -3/10. And now we'll just go ahead and simplify all of this. So I can I can cancel out one of the 5's in my numerator, and I have a 5 squared with the 10 in the denominator. So we're going to end up with a pi, and we're going to end up with a 5 in the numerator times a 3. So that's gonna be 15. So in fact, I'll slide this over a little bit so I can put the 15 in front. Plus we have a negative, so it's going to be -15 pi. And in the denominator, right, we did the 5 here with the 10 here to give us just a 2 down there, times this 4 is going to give us 8. So we have -15 pi over 8. It wants units of measure. Well, this is going to be, since it's a rate of change of the volume, centimeters cubed per hour. And they're going to give us actually 5 total points for this. The first one is if we just had this radius equal to 1/2 h, either in part A or in part B. And then they gave us a point for this. The volume is pi h cubed. Then they gave us 2 points for the correct derivative with respect to time, and 1 for the final answer with units. And here in part C, it says, to show that the rate of change of the volume of water in the container due to evaporation is directly proportional to the exposed surface area of the water. Right? Well, the exposed surface area of our water there, right, is just going to be like pi r squared, right? And so, because that's all we've got exposed is just the top of the cone. So we do know that the volume of the water, as we already looked at before, right? We had dv dt was equal to, we ended up with pi h squared over 4 dh dt. And if we think about that, what we're gonna do next is think about, like, if we can show that using the area formula, right, for our exposed portion, right, that area being pi r squared, if we can get a constant of proportionality there between the two. And of course, we know that dh dt from the previous part of the problem, or not even from the previous part, but just from right here, is -3/10. So I can rewrite this as pi h squared over 4 times -3/10. Well, that looks like -3 pi h squared over 40. And we know that we're looking for pi r squared in here, right? And so the idea is that we've got r, our radius, is equal to 1/2 the height, as we said before, or in other words, h is equal to 2r. So if I replace the h with 2r, we end up with -3 pi of 2r squared over 40. Well, that is -3 pi times 4r squared over 40. And of course, the 4's can cancel out, and we have now -3/10 times pi r squared. And so right there, that shows us that that rate of change of our volume of the water, this is what that is directly proportional to the exposed area of the surface of the water because the surface, the area of that surface is pi r squared. And that tells us that our constant of proportionality must be -3/10. So all we have to do is just take the area of the amount of water that's exposed and multiply it by -3/10, and that will also tell us what the rate of change of the volume of the water is. And so they gave you 2 points for that. One just for going through and showing that we ended up with -3/10 times pi r squared, and one for indicating that -3/10, we'll call it k, is -3/10. So 1 point for that and 1 point for showing that. And that is the end here of question number 5, here a rate FRQ from the 2002 AP Calculus AB exam. All right, this is question number 2 from the 2002 AP Calculus AB Form B exam. And this is a rate FRQ. And so what we've got here is we've got some number of gallons, P of T, of a pollutant in a lake. It's changing at a rate given by P prime. And we know that at the beginning there are 50 gallons of this pollutant in the lake, and that the lake is considered safe when it contains 40 gallons or less. We want to know, is the amount of pollutant increasing at time t equals 9, first of all? Well, the amount is the P function, and so to find out if P is increasing, we just need to find P prime at 9. This is a calculator question, so we'll just go into our calculator, and we will evaluate P prime at 9. So 1 minus 3 e to the power of -0.2, and then times the square root of 9, square root of t, right? Square root of 9 is 3, and it looks like that comes out to be -0.646, which is less than 0. And so we will say, so the amount is decreasing, or we could say it says, is it increasing? So the amount is not increasing, or we could just say it's decreasing. In the more recent years, they say, is it increasing or decreasing? So we get 1 point there for part A, for your answer with a reason. In part B, we want to know for what value of T will the number of gallons of pollutant be at its minimum. And so what we'll do here is we'll just set P prime equal to 0, because when the derivative of a function is 0, that's when it could be at a minimum or a maximum. And of course, you can do this by hand, or you can just put it into your graphing calculator and do it that way. I'm going to just put it into my graphing calculator. So I'm going to go to y equals, and I'm going to graph this function, which was 1 minus 3 e to the power of -0.2 root t, or in our case, we'll use root x. And so we're just going to graph this, and I'm going to change my window. And I don't think we had a specific endpoint of our interval, so we're just going to start at 0, and maybe just throw this into like 100 and kind of see what's going on here. Well, it looks like it starts below the x-axis, crosses through once, and doesn't look like it's ever going to go back down after that. And if it does, it's probably going to be, it's not going to. This function, if you take a look at it here, this function is always going to be an increasing function, it would appear. And it should be, because it's exponential. So let's just calculate that value. We'll do second trace. We'll look for the 0, option 2. We're going to scroll till we're to the left of that intercept, which is now, because we can see our y values are negative. We'll hit enter. We'll go till our y values are positive to the right, hit enter twice more, and it tells us 30.174 if we round it. And we won't round it here. We'll do 30.173 1 what was it? 724 there? Yeah, 724. All right, and so that's when we're at a minimum. We know we're at a minimum there because p prime of t is, we'll just say, is less than 0 on 0 to 30.173724, and p prime of t greater than 0 on 30.173724 to, well, seems like infinity, right? And so p has a minimum at t equals 30.174. We can just round it to 3 or more decimals. And they give you 3 points there. 1 for getting this value, 1 for getting the value, 1 for just setting it equal to 0, 1 for the value, and 1 for the justification that p prime is negative and then p prime is positive. In part C, it says, is the lake safe when the number of gallons of pollutant is at its minimum? Well, to find the number of gallons of pollutant, we just need to take our initial amount, which was 50 gallons, and then add to that the integral of the rate at which the pollutants change, which is the integral from 0 to that t value we just found, which was 30.174 of p prime of t dt. And so we'll just go back to our graphing calculator. And now it's convenient that we've put this function in, so now I don't have to type it again. We're just going to do 50 plus math. And then option number 9 is the integral. We're going to do 0 to 30.174 of p prime, which we can get by hitting the VARS button and going to the second column and choosing function and then y1, and then putting dx. And that gives us 35.104. Well, the lake is safe when the amount of pollutants is less than 40. This is less than 40. So yes is our answer. And so we get 3 points here for this. 1 for just having the integral set up, 1 for having the right limits, and 1 for our answer with the justification that it's less than 40. All right, in part D, we've got an investigator using a tangent line approximation to P of t at t equals 0 as a model. And we want to know at what time t does this model predict that the lake becomes safe? Well, to do a tangent line approximation, we just need a point, and the point we're going to use is the point 0, 50. And then we want to find the slope. Well, the slope is just going to come from finding p prime of 0, and that's going to be 1 minus 3e to the 0, which is just going to be negative 2. So our equation should be y equals negative 2x, or we'll say negative 2t, plus 50, just in slope-intercept form, our slope and our y-intercept. And so we want to know when is this less than 40, or so now we just solve this for t. Well, subtract the 50, we get negative 2t. Or really, we're just looking not for when it's less than 40. We just want to know when this hits 40, right? And so we'll just subtract the 50, and negative 2t equals negative 10, and t is equal to 5 is when it hits that value of 40. We knew we were above to start with, so now it's going to be below once we hit t equals 5. And you got 2 points here, 1 for the slope of the tangent line and 1 for the answer. And that is the end of this rate FRQ, question number 2 from the 2002 Form B AP Calculus AB exam. All right, this is question number 3 from the 2003 AP Calculus AB exam. This is a rate FRQ, where we're given a rate of fuel consumption in gallons per minute for an airplane. It's twice differentiable and strictly increasing. And we have a graph of R and a table of selected values of R on the interval 0 to 90. We want to approximate R prime of 45 using the table. So to approximate the derivative of something, we just usually want to do an average rate of change on the smallest interval surrounding 45. So that's going to be from 40 to 50. So we'll do 55 minus 40, the R of t values at 50 and 40, divided by 50 minus 40, which just gives us 15 over 10, which is, of course, 1.5 or 3/2. And our units here are going to be, the original units were in gallons per minute, but if we divide by time again, that'll be gallons per minute squared. And they gave you 2 points here for that, 1 for the answer and 1 for the units. In part B, it says the rate of fuel consumption is increasing fastest at t equals 45. And we want to know what is the value of R double prime of 45. Well, if the rate is at its fastest increase, so if the rate is increasing fastest, that means the rate is at a max. Well, if the rate is at a max, that means that its derivative should be, if the rate is, if the rate is increasing at its max, so we're going to say not the rate is at its max, but the rate increase is at a max. That's a little bit different. The rate increase, that's R prime, the rate at which the rate is increasing. And if that rate is at a max on a twice differentiable function, that means that the second derivative has to equal 0, right? Because there can't be a place where the second derivative is undefined if R is twice differentiable. So R double prime of 45, and we should be a little more clear about that, R double prime of 45 should be equal to 0. And it says explain your reasoning. Well, our reasoning is that R prime has a max there, right? And R is twice. So R prime has a max, and R is twice differentiable. And if it's twice differentiable, its second derivative cannot be undefined. And they gave you 2 points here for this, 1 for 0 and 1 for the reason that it has a max and that it's twice differentiable. In part C, it wants us to approximate the value of the integral from 0 to 90 of R. And then it wants us to do that with a left Riemann sum with 5 subintervals, and then determine if that's less than the actual value. So first we'll do the Riemann sum. So the first interval from 0 to 30 is 30 minutes. So we'll do 30 times the left endpoint of that, which is 20, right? 0 to 30 is 30, and the left endpoint is 20, the value at 0. We'll add to that the 30 to 40. 30 to 40 is 10 units. And we'll multiply that by the next left end unit. So that's 30. And then we'll do 40 to 50, which is 10. And at 40, it is 40. So that'll be a 40. From 50 to 70 is 20. And now we'll use 55. And from 70 to 90 is 20. And now we'll use 65. And this is a calculator question, so you can go ahead and use your calculator to total all that up if you want. It comes out to be 3,700. And since we know that R is increasing, when R increases, when a function increases, the left rectangular approximations always lie under the curve. So we can say that this is an underestimate because R is increasing. So that is worth 2 points. 1 for the value and 1 for underestimate because it's increasing. And in part D, it says from 0 to 90 minutes, what is the integral from 0 to b of r in terms of fuel consumption for the plane? What does that mean? Well, if you integrate rate, it gives you an amount. So we can say the integral from 0 to b of r of t dt is the total amount of fuel consumed by the plane in those b minutes. And it also says explaining the, and actually it tells us to indicate units of measure. So total amount of fuel, and this will be in gallons. And our other unit was minutes. So make sure you say that. And then the other one, which I'm just going to go to another page for this because I don't really have any room here. 1 over b times the integral from 0 to b of r of t dt. Well, that's 1 over b minus a times the integral from a to b of the function. So that is the average value of the rate it's being consumed. So it's the average rate. Fuel is consumed in, and this is, our units were gallons per minute. So in gallons per minute by the plane during those first few minutes, during those first b minutes. And they'll give you 3 points here. 1 for having the units in both of them, right? Right here's the units also. And then 1 for each explanation. So 1 for this explanation and 1 for this explanation. And that's the end of this rate FRQ, question 3 from the 2003 AP Calculus AB exam. All right, this is question number 2 from the 2003 Form B AP Calculus AB exam. It's a rate FRQ. We've got a tank with 125 gallons of heating oil at t equals 0. And from 0 to 12, oil is pumped into it at this rate h of t in gallons per hour. And it's also removed at this other rate r of t, also in gallons per hour. We want to know how many gallons of heating oil are pumped into the tank from 0 to 12. Well, in order to figure out how much is pumped in, not how much is in the tank, but how much is pumped in, we just integrate the rate at which it's being pumped in on the interval that we're interested in. So we're just going to do an integral from 0 to 12 of h of t dt. And this is a calculator question, so we're just going to use our graphing calculator here to find that value. So we're going to hit math. We're going to go down to option number 9, FNINT. We'll put our limits of 0 and 12, and then we'll just type in that h of t function, which was 2 plus, and then a big fraction. And I always like to do alpha x to give us this nice little fraction bar. We've got a 10 in the numerator, and in the denominator, we've got 1 plus the natural log of t plus 1. Oh, we missed our 1. We've got 1 plus the natural log of t plus 1, and we'll just use x because that's what we use on our calculator here. And then we'll throw in our dx here, and we'll let our calculator evaluate that to be 70.571. So it's approximately 70.571 gallons. And you got 2 points here, 1 for the setup and 1 for the answer. In part B, it asks, is the level of the heating oil in the tank rising or falling at t equals 6? Well, that depends on its rate of change. So are we pumping in more oil than we're removing, or are we removing more oil than is being pumped in? In other words, is the rate at which it's being pumped in minus the rate at which it's being removed greater than 0 or less than 0. So that's what we're interested in, is it positive or is it negative? So let's just evaluate h of 6 minus r of 6, and that ought to tell us whether it's positive or negative. It should tell us if it's rising or if it's falling. And so we'll just go to our calculator again here. H was 2 plus that fraction that we get with alpha x, 10 over 1 plus the natural log of our value 6 plus 1, so the natural log of 7. So that's h of 6. And then we're going to subtract r of 6, which is 12 sine of t squared, or x squared in our case, which if we're using 6 will be 36, over 47. And if we subtract that, we get negative 2.924. So we'll say that's approximately negative 2.924. And we will say that that's less than 0. So the level of oil is falling. It's going down, right? We're removing more oil than is being pumped in. And they just gave you 1 point here for the answer. And of course, you have to have some work to back it up. In part C, it wants to know how many gallons of oil are in the tank at t equals 12. Well, all we have to do here is just do the initial amount, 125, and then integrate the amount to find the amount that's gone in on 0 to 12, h of t dt's integral, and then subtract the amount that has been removed on that integral, or on that interval. So we already did the integral from 0 to 12 of h in part A. So when we go back to our calculator here, I'm just going to go up and find that value, so I don't have to retype it all, and hit enter, and that brings that value down. And then we're going to add our initial condition of 125 to that. And then what we want to do is we want to subtract that integral from 0 to 12 of r of t. So we'll just hit minus. That'll use our previous answer. We'll hit math. We'll go down to option number 9, and we'll just do an integral from 0 to 12 of that r of t function. And r of t was 12 times the sine of x squared over 47. And we'll throw our dx out there. And when we hit enter, it looks like we get 122.026 gallons. And for this one, they gave you 3 points. 1 for having the appropriate limits. 1 for having the integral. And since we had 2 separate integrals, the scoring guidelines might have put it as 1 integral. You probably didn't even need to write this integral out. You could have just said 125 plus the answer from part A. You could have just written that answer out and then subtracted the integral from 0 to 12 of r of t from it, like we did. And then 1 point there for the final answer. And our last part here, in part D, says, at what time is the volume of the heating oil in the tank the least? Well, we know that the oil in the tank, the amount of oil in the tank is always, and let's call it A of t, is always 125 plus the integral from 0 to 12 of h of t minus r of t, or the integral from 0 to 12 of h of t dt minus the integral from 0 to 12 of r of t dt. You can do 2 separate integrals if you want. So in order to figure out when a function, a of t, is at its minimum, so we want to take its derivative and find the critical value. So we'll say a prime of t. Well, a prime of t is just the derivative of this. The derivative of 125 is 0. And the derivative of an integral, oh, and this shouldn't be a 12 up here. That should be some value. We'll call it t. And what we'll do actually is we'll just change these all into x's, a dummy variable in here. Just kind of moving a little too quick here. an integral from 0 to t of h minus r. And so when we take the derivative of the integral from a constant to a variable of a function, we just get the function in terms of that new variable. So to find when we're at a minimum, we just set a prime, or h of t minus r of t, equal to 0, which means we need to go back to our graphing calculator, hit our y equals, and we'll graph h of t minus r of t. So h of t was 2 plus this nice little fraction by hitting alpha x first, and then 10 over 1 plus the natural log of x plus 1, and then minus 12 times the sine of x squared over 47. And we're going to graph this, since this is on 0 to 12, we're going to hit window, and we're going to change the x minimum to 0 and our x maximum to 12. And then we'll graph and see that our derivative, h minus r, is positive for a while, until we get to this value at 4 point something, right? And we'll do second trace and find that 0, option 2, 0. And we'll go to the left and hit enter. We'll go to the right and hit enter. We'll hit enter a third time and see that that's 4.790. So we'll say this is true at t is 4.790. And then we'll go back and find the other one. Again, second trace, option number 2 for 0. And we'll go way over here, close to that second one. Hit enter, go to the right of it, hit enter, and hit enter a third time to get 11.31847. We'll just call it 11.318. And we'll note that because h of t minus r of t, which is a prime of t, is greater than 0 on 0 to 4.790, a is increasing, right? And we can see that right here in our graph. And then we know that below that we're negative, so we can say that a prime is less than 0 on 4.790 to 11.318, so a is decreasing. And then finally, we also know that a prime is, again, greater than 0 on 11.318 to 12, so a is increasing. And that tells us that our minimum can only occur at 0 or 11.318. So we'll say, so min is at t equals 0 or t equals 11.318. Well, a of 0 we already knew was 125. So now we just find a of 11.318, which is 125 plus the integral from 0 to 11.318 of r of t minus, or that's h of t minus r of t. And so we'll just use our calculator here. We'll do 125 plus math, option 9, the integral from 0 to 11.318. And now instead of retyping this whole function, we can just hit VARS, the button just next to the clear, go over to the second column, choose option 1 and y1, because that's where we've saved that function when we graphed it. And we'll integrate with respect to x here. We get 120.738. It's less than 125. So the minimum volume occurs at t equals 11.318. And we got 4 points there for that. We got 1 point for just setting h minus r equal to 0, right here. We got 1 point for the correct thing. Let's see here. No, we have 3 points for this. Sorry, 1 for h minus r is 0, 1 for the volume is least at this 11.318, and 1 for our analysis, which includes this and this statement. And of course, you could have evaluated it at the endpoint of 12 and 4.790 also and just picked the smallest one. But doing this little analysis allows us to only have to test 1 or 2 different values. And that's the end of this rate FRQ, which is question number 2 from the 2003 Form B AP Calculus AB exam. All right, this is question number 1 from the 2004 AP Calculus AB exam. It's a rate FRQ, and they tell us that we have a traffic flow defined as a rate at which cars pass through an intersection in cars per minute, and they give us a rate, capital F of t, for some particular intersection. And we want to know to the nearest whole number how many cars pass through the intersection over the 30-minute period for which this function is defined. Well, if we're given the rate at which they are passing through the intersection to find how many actually pass through, we just need to integrate that rate from 0 to 30. So if we just, since it's a calculator question, we're just going to go to our calculator and hit math. Option number 9, FNINT, brings you an integral. You'll put 0 as your lower limit, 30 as your upper limit, and you'll type in your function, which was 82 plus 4 times the sine of t over 2. On our calculator, we're just going to use x, so x over 2, and then we have a dx. And that comes out to be 2,474.078 if we round. And we will say 2,474 cars because it asked us to round to the nearest whole number. And you got 3 points here for part A. 1 for having the right limits of integration, 1 for having the right function that you're integrating, and 1 for having the correct final answer. In part B, we're asked, is the traffic flow increasing or decreasing at t equals 7? Well, the traffic flow is F, and so we want to know, is F increasing or decreasing at 7? So we need to find F prime of 7. F prime will tell us if it's increasing or decreasing, whether it's positive or negative. So again, this is a calculator question. So we're just going to use our calculator to find that derivative. We're going to hit math. We're going to go down to option number 8 this time, in deriv. And we're going to do a derivative with respect to x of our function, 82 plus 4 times the sine of x over 2. And we'll evaluate it at x equals 7, because we wanted to know 7 minutes in. That gives us negative 1.873 when we round. And so we can say, since that is less than 0, we'll say since capital F prime of 7 is less than 0, the traffic flow is decreasing at t equals 7. And they gave you 1 point there for just having that answer with the reason. For part C, it asks us the average value of the traffic flow. Well, to find the average value of a function, you do the mean value theorem for integrals, which says 1 over b minus a, so 15 minus 10, since that's the interval they've given us here, times the integral from 10 to 15 of the function. So again, this is a calculator question, so we're just going to put our function here into the calculator. We'll do 15 minus 10, of course, is 5. So we're going to do, I'm going to hit alpha x. We'll do 1 over 5 here in front. Alpha x gives us that nice little fraction. Then we'll do math option number 9. And now it's the integral from 10 to 15 of our function, once again, which was 82 plus 4 times the sine of x over 2 dx. And that gives us 81.899 if we round, 81.899. And it does say indicate units of measure. Well, this is going to be cars per minute. And we got 3 points there for that. 1 was for having the correct limits again, 1 for the integrand, and 1 for the answer. In part D, it asks, what is the average rate of change of the traffic flow over this time interval? Well, the average rate of change of f of t on 10 to 15, well, average rate of change is just the slope, f of 15 minus f of 10 over 15 minus 10. And so we'll need to find f of 15 minus f of 10, of course, and then just divide it by 5. So we'll go in and we'll type it all the way in here. F of 10 is going to be 82 plus 4 times the sine of, we're doing f of 15 here. So f of 15, 15 over 2 inside of there. So 15 over 2. So that's our value for f of 15. We want to subtract from that f of 10, which is, again, 82, plus 4 times the sine of 10 over 2, which is just 5, which gives us 7.587697006. And then, of course, we needed to divide that by the 15 minus 10, or divide it by 5, which gives us 1.518 when we round. So we'll put 1.518. And it says indicate units of measure again. Well, F was already in cars per minute. And if we divide that by another number of minutes, that's minutes squared. And they gave you 1 point for the answer here, 1.518. And then the 9th point here was for having the correct units in part D as well as in part C. So you had to have them correct in both C and D to get that 9th point. And that is the end of this rate FRQ, question number 1 from the 2004 AP Calculus AB exam. All right, this is question number 2 from the 2004 Form B AP Calculus AB exam. It's a rate FRQ. And we've got from t equals 0 to 31, a rate of change of the number of mosquitoes on an island is modeled by this function r of t. And we know that there are 1,000 mosquitoes at t equals 0. And we want to show that the number of mosquitoes is increasing at t equals 6. So in order to do that, we just need to find r of 6, because r of 6 will represent the rate of change of the number of mosquitoes. So if it's positive, that is going to be increasing, and if it's negative, it's going to be decreasing. So since this is a calculator question, I'm just going to go in and input 6 here into my function, 5 square root of 6 times the cosine of t over 5, so 6 over 5. And we'll see that that comes out to be 4.438 if we round it. And so we'll say it's about 4.438, which is greater than 0. So the number of mosquitoes is increasing. Right, it's a positive rate of change, therefore it must be increasing. And they gave you 1 point for showing that r of 6 was greater than 0 and saying increasing. Part B, it says that time t equals 6 is the number of mosquitoes increasing at an increasing rate or at a decreasing rate. So to determine if it's an increasing or a decreasing rate, we need to find r prime of 6, right? To determine if a function, which is the increase of the number of mosquitoes, that's the function, right? The rate of change of the number of mosquitoes. If it's increasing at an increasing or a decreasing rate depends on the derivative of that function. So r prime of 6. And so in order to find r prime of 6, we can just use our calculator again. We can hit math. We can go down to option number 8, and we're going to take the derivative of our function r of t, and we'll do it as r of x, 5 square root of x, times the cosine of x over 5, and we're going to evaluate that at x equals 6. And we get negative 1.913, which we note is less than 0, so it is increasing at a decreasing rate because its derivative is 0. We'll say r prime of 6 is less than 0. And they give you 2 points for that, one just for considering r prime of 6 at all, and one for the answer with a reason. In part C, it says, with this model, how many mosquitoes will be on the island at t equals 31? Well, we knew there were 1,000 mosquitoes initially, so we have those 1,000, plus the integral of the rate of change of the mosquitoes. So the integral of r of t dt from 0 to 31. And so we just are going to, again, just use our calculator here to evaluate this. So we'll do 1,000 plus math, option number 9, and it'll be an integral from 0 to 31. 31, there we go, of r of t, which again is 5 times the square root of x times the cosine of x over 5 dx, and it comes out to be 964.335. And it says to the nearest whole number, so 964 mosquitoes. And 2 points there, one for having the integral and one for the final answer, rounded to the nearest whole number. And here in part D, it says, what is the maximum number of mosquitoes on this interval from 0 to 31? So we need to see when the derivative of a function representing the number of mosquitoes is equal to 0. Well, the function to represent the number of mosquitoes, of course, is just the 1,000 plus the integral from 0 to t of that rate function. And so the derivative of that, m prime, is just r of t. So we just want to know when does r of t equal 0? And those are the locations at which we can have a maximum or a minimum, and then we will we'll go ahead and figure out which one's actually the maximum. And this is a calculator question, so you can graph this and find those values. Or you can also just solve this, right? We know that it's going to equal 0 when t is 0, because that'll give us the square root of t equal to 0, or when cosine of t over 5 is equal to 0. Well, the cosine of t over 5 equaling 0, that's going to happen whenever the angle is pi over 2, right? Because cosine is equal to 0 at pi over 2, plus any pi n. So if we just multiply by 5, we'll get t equals 5 pi over 2 plus 5 pi n. So we just look for the values that are between 0 and 31. So if n is 0, that gives us 5 pi over 2. And if n is 1, n is 1 is going to give us 15 pi over 2. And n being 2 is going to give us 25 pi over 2. Well, 25 pi is, is more than 25 times 3. It's more than 75. And 75 divided by 2 is already more than 31. So these are our 3 critical values. And of course, we'll also check the endpoint t equals 31. And so we can just find the largest value by either evaluating our function at all 4 of these values, which is pretty straightforward with our calculator, or we can make a sign chart to determine which one is actually minimum or a maximum, right? So we're going to kind of just do both here. I'm going to graph my function 5 square root x cosine of x over 5, right? That's our derivative. We're going to graph it on the window. So I'm going to hit window and from 0 to 31. And when I graph that, I can see that it started out positive, then it was negative, then it was positive. So if the derivative is positive, then negative, then positive, right? That means that our function is increasing, then decreasing, and then increasing, which means that we're not going to have a maximum at 0, we're going to have a minimum, because after 0, our function increased. So we could have a maximum at that first value there of 2.5 pi, or 5/2 pi, or then we have a minimum over here at this other value, and then at the end of 31, we have another maximum. So our maximum, and if we think about that, like let's just kind of write that down. We won't actually test all 4 because that seems like it's overkill. We know that r of t was greater than 0 on 0, not with a bracket, with a parenthesis actually, a parenthesis, 0 to 5 pi over 2. And we also knew that r of t was less than 0 on 5 pi over 2 to 15 pi over 2. And we also know that r of t was, again, greater than 0 on 15 pi over 2 to 31. So that tells us that our max could only be at 5 pi over 2 or at 31. Well, if we logically think about this, at 0, we knew it was already 1,000, right? And if I go back here, we found that at 31, it was only 964. So our other option of a max, we knew it was 964, which was less than the 1,000 that we already had at t equals 0. So our only possibility here is going to be that the maximum occurs at 5 pi over 2. And so now we'll just evaluate this function m at 5 pi over 2. We've kind of run out of room here, so we'll do this on a new page. M of 5 pi over 2 is just 1,000 plus the integral from 0 to 5 pi over 2 of r of t dt. And so we'll do this on our graphing calculator. We'll hit second quit to go back here. And the nice thing is we've already basically typed this whole thing in, except with the wrong upper limit. So if I just highlight that and hit enter, it brings it in, and I can just go back, and instead of having a 31, I can put in 5 pi over 2. And now we can evaluate that, and we get 1,039.357, which we can see is bigger than the 1,000 and bigger than that other place where we had the maximum. So our maximum is 1,039, and it occurred at 5 pi over 2. We got 4 points for that part. So the first point came from the doing the writing out like that we need to do this integral here. The second point came from actually having the answer right here. And then the third and fourth points came from the analysis, which was finding all of these values and then talking about why it had to be either 5 pi over 2 or 31, and then why we eliminated 31 as a possibility. Or we checked 31 and said, oh, it's 964, and that's less than 1,039. And that is it for this rate FRQ, which was question number 2 from the 2004 Form B AP Calculus AB exam. All right, this is question number 2 from the 2005 AP Calculus AB exam. This is a rate FRQ. It's a calculator question. And we've got Tide removing sand from Sandy Point Beach at a rate modeled by R of T. And then we have a pumping station adding sand at a rate given by S of T. The units are cubic yards per hour. T is hours from 0 to 6. And we have an initial condition that initially the beach had 2,500 cubic yards of sand at T equals 0. And part A just asks, how much sand will the tide remove from the beach during this 6-hour period? Well, the question isn't asking what's the change in the amount of sand or how much is removed and added or how much is there. It just says how much will it remove. So all we have to do is integrate our rate at which it's being removed, or R of T, dt, on the interval from 0 to 6. And since this is a calculator question, we'll just go into our calculator. Our graphing calculator here, we're going to do math. Option number 9, we could just hit the 9. We're going to integrate from 0 to 6, and we'll just type in our R of T function, which is 2 plus 5 sine of, and I like to do the alpha and the x button right next to it to give me this nice fraction. It's 4 pi t, or we'll use x, 4 pi x over 25. And we'll throw our dx out there at the end. And we get 31.816. And it does say indicate units of measure. And so how much is being removed is in cubic yards, or you can just say yards cubed, whichever you prefer. 2 points here for part A, 1 for the integral setup and 1 for the answer with appropriate units. In part B, it says write an expression for y of t, the total number of cubic yards on the beach at time t. Well, y of t then should just equal the amount that we started with, the initial condition, so 2,500, plus the amount that it changes, right? So we're adding s amount, so an integral of s, which we'll do from 0 to whatever t value we're interested in. So we'll put a dummy variable in here. I'll use x, so s of x. And then we're subtracting the amount that is being removed, so we'll integrate the rate there that it's being removed. So we have just 2,500 plus an integral from 0 to t of s of x minus r of x dx. And they actually gave you 3 points just for writing that. 1 for having the appropriate integral, and you could, of course, separate it into 2 integrals if you want. 1 for having limits of 0 to t, and 1 for the whole thing as an answer that you actually wrote y of t equals and had the initial condition. All right, part C says, find the rate at which the total amount of sand on the beach is changing at t equals 4. Well, we already know that y of t is the total amount, so its rate of change will be y prime at 4. And so all we have to do then is just evaluate y prime of 4. And if I was doing the AP test, I'd probably look ahead here for a second, right, before I actually evaluate this, which we'll do in a second. Let's look ahead. And part D says, when is the amount of sand on the beach at a minimum? Well, the amount of sand is y. It can be at a minimum when its derivative, y prime, is equal to 0. So we're going to have to graph y prime, which means we're going to have to type it into our y equals screen anyway. So what I'm going to do is I'm going to just do that right now. I'm going to hit y equals, and our y prime is s minus r. And in fact, we didn't actually write that out. Y prime is s of 4 minus r of 4. And that's not actually the approximately equal there. That's exactly what it equals. And we're going to find that in a second. So we're going to graph s minus r because we need to know when that equals 0. So s, I'm going to hit alpha x to get me this nice fraction. It's 15t, or 15x, over 1 plus 3x. And then minus our r, I'm going to put it in parentheses, 2 plus 5 sine. And again, I like to hit alpha x to give me this nice fraction. 4i x over 25. Close the parenthesis for the sine and for the subtraction. And we're eventually going to need to graph this, and we'll just graph it for right now. That's what it looks like, and we'll deal with the window in a second. We wanted to know the value of that for part C at 4. So rather than having typed that all into our calculator, we can just hit second, trace, and choose option 1 for value, and just type in a 4. It'll tell you that at x equals 4, you get negative 1.908751, or negative 1.909. And now you don't have to type that function multiple times. Right? You've already got it in there. So negative 1.909, and we could put units here. It's yards cubed per, I believe it was hour, right? Yep, yards cubed per hour here. So now that we've already looked ahead to part D, let's give our points here. We got 1 point here for the answer. Now that we've already looked ahead to part D, we were looking for when the amount of sand on the beach is a minimum on 0 to 6. So that can happen when our derivative, or s minus r, is equal to 0. So we've already graphed s minus r. Now I'm going to change my window so that I'm only looking from 0 to 6, because I don't really care about what's happening other than that. So now I can see just the portion of my function from 0 to 6. And we can see that our derivative here, which is s minus r, what we've graphed, the derivative of y prime, is negative all the way into that x-intercept. So if the derivative is negative, that means the value of y is decreasing on that entire interval until we get to our x-intercept. Then the derivative is positive, so the function is increasing after that. So when we find that intercept by hitting second, trace, and option 2, 0, right? We'll find it first, and then we'll kind of do a little analysis here. So we go over here. We'll get closer, maybe. It doesn't really matter. That's close enough. Hit enter on the left. Hit enter on the right. And hit enter again, and we get 5.1178653. So we'll note that y prime of t is equal to 0 at t equals, our value is 5.1178653. So that's where we could have a minimum. And in fact, we know that we have a minimum there because we can make the statement that y prime of t is less than 0 on, and I'm just going to call this some value q. So I'm going to say y prime is negative on 0 to q. So y decreases. And I'm going to say y prime is positive on q to 6. So y increases. And if I decrease and then increase, that tells me that so y of t has a max at q. And oftentimes they just test the values at every critical value. But if you write this little analysis showing that, not a max. We have a minimum there, right? If we're decreasing and then increasing, we have a minimum. So I don't know what I'm thinking there for a second. If y decreases, then increases, we're at a minimum at q. And so we just want to find y of q, right? Because we know that the endpoints can be eliminated as options because they're both larger than where we were at that minimum. So the min is y of q, and we'll find y of q back on our graphing calculator. Right? Y of q should just be the, remember y was the initial amount, which was 2,500, and then plus the integral of the function we have graphed as y1. So we'll do plus, we'll do math, and we're going to do option number 9 here. And we're going to integrate this from 0 to that value we had of q, which was 5.1178653. And I don't have to retype the whole function. I can just hit the VARS button just to the left of clear, go to the second column and do option 1. And option 1 for y1 just takes that function I've already typed in, so I don't have to retype it. Put my dx, and we end up with 2,492.369 when we round. And so we'll put that in, 2,492.369, and our units were cubic yards. And that gives us the last points here for this question. 3 points, 1 for just setting y prime equal to 0, 1 for getting this t value, and 1 for an answer with the justification where you either tested 0, q, and 6, or you just did the minimum at q with this analysis about y decreasing and increasing, so the minimum had to be at q. And that is the end of this rate FRQ. It was question number 2 from the 2005 AP Calculus AB exam. All right, this is question number 2 from the 2005 Form B AP Calculus AB exam. This is a rate FRQ. We've got water in a tank at Camp Newton. It holds 1,200 gallons of water at time t equals 0. We've got a rate W of t at which water is pumped into the tank, and a rate R at which it's removed from the tank, both in gallons per hour. We want to know is the amount of the water in the tank increasing at t equals 15. And so if the amount is increasing, its rate of change would have to be positive. Well, its rate of change is just W of 15 minus R of 15. That should be the rate of change of the amount of water in the tank, right? The rate at which it's being pumped in minus the rate at which it's being pumped out or drains out or whatever's happening. It's being removed. So we'll just evaluate W of 15 minus R of 15 just using our graphing calculator since this is a calculator question. So W was 95 times the square root of t, so 95 root 15 times the sine squared of t over 6. So we'll do, since the function on the calculator doesn't have a sine squared function, we'll just do the sine of 15 over 6, close the parentheses on the whole sine, and then square that. So that's W of 15. And then we'll subtract from that R of 15. Well, R was 275 times sine squared of t over 3, so we'll do the same thing, parentheses for the sine of 15 over 3, we could just put 5, of course, and then close the parenthesis for the sine and square it to get it to be a sine squared, and we end up getting negative 121.090. So we'll note that value is it's approximately negative 121.090. So no, it is not increasing because W of 15 minus R of 15 is less than 0. And they just gave you 1 point here for having the answer of no with the reasoning. So that's it there for part A. In part B, it wants to know to the nearest whole number how many gallons of water are in the tank at t equals 18. Well, the number of gallons in the tank at any given time is going to be the initial amount, which was 1,200, plus the amount that is pumped in. Well, the amount that's pumped in is an integral of the rate. So it's going to be an integral of W of t dt from 0 to 18. And then minus the amount that's pumped out. So that's going to be an integral from 0 to 18 of the rate at which it's pumped out. So all we need to do is use our calculator here to figure out what that value is. So we'll go into our calculator. We'll do 1,200 plus, and then it'll be math, option number 9 to get your integral. And our limits are 0 to 18. And since it was 0 to 18 of both functions, right, one minus the other, I can put them both inside the same integral if I want to, or I can do them separately. I'm just going to put them both into the same one. That way I don't have to redo the integral portion. So W of t was 95 times the square root of t, so we'll do 95 root x, because that's what we have to do on our calculator. And again, for the sine squared, we'll start a parenthesis for the sine. We'll put in our t over 6, which we'll use x over 6. Close the parenthesis of the sine and then square it to get the sine squared. So that's W of t. And then we're going to subtract from that R of t, which was 275 times the sine squared of x over 3. So we'll have the sine of x over 3. And then we want to square that whole sine. And then we'll just throw our dx out at the end. When we integrate it, we get 1,309.788. It said to round to the nearest whole number, so that'll be 1310. So we'll say this is approximately equal to 1,310 gallons. And they gave you 3 points there for doing that. 1 for having the correct limits of 0 to 18. 1 for the correct integrands, W minus R, and 1 for the final answer. In part C, it asks us at what time t is the amount of water in the tank at a minimum. Well, we already knew that the amount of water in the tank was this function that we just had. I'll call it A of t, right? The amount of water in the tank was just 1,200 plus the integral from 0 to t of W minus the integral from 0 to t of R. So to figure out when a function, in this case a function that represents the amount of water in the tank, is at a minimum, take its derivative. Right? And then find the critical values. The derivative of 1,200 is 0. The derivative of an integral from a constant to t of a function is just the function in terms of t. So that applies to both W and R. So we are just looking at W of t minus R of t. So we want to know, when does that equal 0? And so we'll those are our critical values, right? And so what we'll do is we'll just go in and we will graph in here y equals, and we're just going to do W minus R. We'll graph W minus R and look for its x-intercepts. So once again, W was 95 times the square root of x, and then it was the sine of x over 6 squared, and then R was 275 times the sine of x over 3, and that was also squared. And I'm going to hit window up here in the top left, and I'm going to change my x minimum to 0 and my x maximum to 18, because that was the interval that we were looking at here. So now when I graph it, I'm only going to be seeing things on 0 to 18. And so I've got 2 x-intercepts here other than at 0, right? And the one at 0 is an endpoint, so I already need to check that. So I'm going to do second, and then trace, and I want 0, option number 2, right? The x-intercepts here. So it starts me at 9. If we look there, it says underneath where it says left bound, we have x equals 9. So we're going to have to scroll to the left till we see our cursor. There it was. And And we're going to, since we're now we want to be to the left of that intercept, we're going to hit enter. And now we're going to go to the right of that intercept, and we're going to hit enter. And we'll hit enter a third time, and it's going to tell us that that is at 6.4948402. So 4948402. And then we're going to find another place here. We'll go back to our calculator. We'll hit second trace. Option number 2 for 0. Now we'll go to the right until, and since we can only see a little bit of our function, kind of keep an eye on the y values. We're getting smaller now on the y values. If we don't, there's our cursor just to the left, so we'll hit enter. Go to the right. We can see now we have a negative y value. We'll hit enter. Hit enter again, and we get 12.974825. And of course, we also want to check the endpoints of t equals 0 and t equals 12. Now, we could go through and just make a chart with all 4 values, or we could do a little bit of analysis and note that on our graph, our derivative, and we're looking for a minimum, right? Our derivative was negative, which means the rate of change was going, it was going down. The amount of water was going down. The rate of change was negative from 0 to that first x-intercept. But then after that, on that second interval from the 6.4 value to the 12.9 value, our derivative here is positive, right? It's above the x-axis, which means that at the end of that, we're going to have a maximum, right? When the derivative goes from positive to negative 12.974825. And we're also going to have a maximum at t equals 0. So we don't really need to test t equals 0 or t equals 12.975. Now you can, but if you don't test them, we're going to make a little statement that says, we'll say a prime less than 0 on t, we'll say 0 less than t less than 6.495. So t equals 0 is a max. And we'll also say, a max on a. And then we'll say a prime changes from positive to negative at t equals 12 point, I'm sorry, this was supposed to be an 18. Now that I just looked down, I wrote t equals 12. We're checking our endpoints. T equals 0, t equals 18. A prime changes from positive to negative at 12.974825. So A has a max there. So our only 2 minimum possibilities are 0 and at 6.4948402. So we're going to evaluate A of 0. Well, we know A of 0. A of 0 is how much was in there at the start, which was 1200. And then we're also going to find A of 6.4948402, which just means we're going to plug that in for t up here in our integral. And so the nice thing here is I've already got w minus r graphed. So I can just go back here and say I want 1200. And then I want to, that because that was my initial amount. And then I want to add to that math and option number 9, the integral from 0 to, what was our value there? It was 6.49, I don't even remember now. What do we have? 6.4948402. So 6.4948402 of that function that we've graphed as y1. So we can hit VARS just next to the clear, just to the left of the clear button. Go over to the second column, y VARS, hit option 1 for function and option 1 for where we have it graphed, y1. And we don't have to retype that whole function again. and then just put an x at the end, and we end up getting 525, because it did say to, well, actually it didn't say to round, so we'll just say 525.242. And so clearly that's less than 1200, and we already stated that the other two values indicated a max, and so we will say the water in the tank is at a minimum at t equals 6.495. We can round that there. And they gave you 3 points for that. So 1 for just finding these critical points, 1 for the statement that it's at a minimum at 6.495, and 1 for the analysis that it's the minimum, which needs to include either testing all 4 values, which we didn't do, or a statement why we eliminated 2 of them and then tested the other 2. So you can either eliminate some as maxima and only test the potential minima, or you can just test all 4 and find the one that's the minimum. All right, the last part of this one, part D, it says for t greater than 18, no water is pumped into the tank, but water continues to be removed until the tank is empty. K is when the tank is empty. We want to write, but we don't have to solve, an equation that involves an integral that can be used to find the value of K. Well, now we're just integrating from 18 to K, the rate at which it's being removed. So r of t dt. Well, we just want that integral, the amount that's removed, to equal the amount that was in the tank at t equals 18. And so if we go back here to part B, we can just use this approximation that we found here of 1,310. So we'll just say this integral needs to equal 1,310, because that's how much we needed to remove. And they gave you 2 points for that, 1 for the limits of 18 and k, and 1 for the equation as a whole. And that is the end of this rate FRQ, which was question number 2 from the 2005 Form B AP Calculus AB exam. All right, this is question number 2 from the 2006 AP Calculus AB exam. This is a rate FRQ, and we're given a graph of a function L of t that represents the number of cars, the rate at which cars turn left at an intersection in a city in Oregon. And we're given this in cars per hour over the interval from 0 to 18 hours. And we want to the nearest whole number to find the total number of cars that turn left at this intersection on this interval. Well, in order to figure out a total number when given a rate, you just have to integrate the rate. So we're just going to integrate L of t dt from 0 to 18. And since this is a calculator question, we'll just go ahead and use our graphing calculator to do this. We're just going to hit math. We're going to go down to option number 9, FNINT, and hit enter, or you could just hit the 9. And now we'll just input our things here. We're going to integrate from 0 to 18, and our function is 60 times the square root of t. So our calculator will use x for that, square root of x, and then times sine squared of x over 3. Your graphing calculator doesn't quite do a sine squared, so you just put a parenthesis and do a sine of x over 3, and then square that. And so then we'll go in and say dx there at the end, and when we integrate this, we should get 1,657.8. It said to round to the nearest whole number, so that'll be 1,658 cars. And they gave you 2 points for this, 1 point for the setup with the integral and 1 point for the answer. In part B, it says that we've got some traffic engineers here that are consider making turn restrictions when L of t is greater than or equal to 150. So we want to find all values of t for which L of t is greater than or equal to 150, and then compute the average value of L over this time interval. So first of all, to figure out when L of t is greater than or equal to 150, we have to see when is L of t equal to 150. And in order to do that, we'll just go into our graph here, and we're going to go into our y equals, and we'll graph L of t. So L of t was 60 square root of x, and then it was the sine squared again of x over 3. So we'll do sine of x over 3, and then we'll square that. And we also want to graph 150. Now you could graph the function minus 150 and look for the x-intercept, but because it's asking us later on to find the average number of cars that make that left turn, right, the average value of L on that interval, it's going to be nice to have y1 as our actual function, so we can just input that and not have to retype the function repeatedly. So I'm going to change my window here. Now I know my x minimum is going to be 0, and my x maximum is 18 because that's the interval we were looking at. And if you look at the graph that they gave you, all the values were above 0, of course, because we're not going to have negative cars turning left. And the highest value they had on there was maybe around 250. So we're going to change our y max to 250. And we should be able to see that our graph now looks pretty much like the graph that was given to us, except now we have this y equals 150 line that's drawn through it. And so we'll calculate those intersection points by hitting second, trace, and then we're going to do option number 5, and you can just hit the 5, or you can scroll down to it for intersect, and that'll find where two functions intersect. So we'll just scroll over to the right a bit till we're fairly close to that intersection point, that first one, hit enter. And then on the second curve, just kind of go over past the intersection point and hit enter, and then hit enter once more. And we get 12.42831 as one of our intersection points. So we'll say t equals 12.48231. And then also t equals, and we'll go back to our graph. We'll do the same thing, second trace, option number 5 for intersect. Now just scroll over close to the other one, hit enter, go a little past the other one, hit enter, and a third time hit enter, and you got 16.121657. So those are the two times when we're equal to 150. So we'll say that L of t is greater than or equal to 150 on the interval from 12 point, and that's not a 12, let's try that again, 12.48231 to 16.121657. And then it just asks us to compute the average value of L on this time interval. Well, the average value of L is just 1 over b minus a. And I don't want to keep writing these, and they usually do this in the scoring guidelines. I'm going to call this A, and I'm going to call this B, just so I don't have to keep rewriting these. So it's going to be 1 over b minus a times the integral from a to b of L of t dt. And you can even store those values in your calculator if you want to, but just having to type them twice isn't going to be so bad, so I'm not going to bother unless we find that we have to use them over and over again in part C. Hopefully that won't be the case. So we're going to do second quit to go back to our original screen. I like to do alpha and then our nice little fraction. We're going to do 1 over the b value, which was 16.121657, minus the a value, which was 12.42831. And then we are going to do math option number 9. And we're going to get our integral. We're going to integrate from 12.42831 up to 16.12167. And instead of retyping the whole function again, I'm just going to hit the VARS button, which is just to the left of clear. And when I go in there, I'm going to go over to YVARS, choose option 1 for function, and we graphed our L function as y1, so we're just going to pick y1. We'll go over here and hit x for our dx, and we end up getting 199.426 cars per hour on average on that interval. And it does say indicate units of measure, so that's going to be cars per hour. We got 3 points here for part B. It says that we got 1 for having the correct interval here, 1 for having this setup, and 1 for the final answer with the units. In part C, it says traffic engineers will install a signal if there is any 2-hour time interval during which the product of the total number of cars turning left and the total number of oncoming cars traveling straight through the intersection is greater than 200,000. In every 2-hour time interval, 500 oncoming cars travel straight. So we know that there are always 500 cars that are traveling straight at this left turn that people are making. And we want to, does this intersection require a traffic signal? And so what we want to do here is we want to figure out if there is any 2-hour time interval on which 500 times our total number of cars that turn left is greater than 200,000. Well, first of all, I mean, let's set this up, right? 500 times the integral from, we'll just call it C, some C to some D of L of t dt. We want to know, is that ever greater than or equal to 200,000? Is it ever, actually not greater than or equal to, but just greater than? Is it ever greater than 200,000? So the question then just becomes, can we find an interval on which the integral from C to D of L of t dt is greater than 200,000 divided by 500? Well, 200,000 divided by 500 is just 400. So we are looking for, is there ever a time interval on which this is more than 400? And so, you know, we could just kind of make some guesses here as to what works, just kind of by looking at our highest values up here, right? Like if I look, we already had this 150, right? That we already said those intervals were from, what was it from? It was from like 12 point something to 16 point something. So I'm just gonna say, well, let's just try a value here real quick. Like something between 12 and 16, but let's say a 2-hour interval in there is 13 to 15. So let's just see what the integral from 13 to 15 of L of t dt, because that's going to be pretty much, like if I look at here, 13 to 15, that's going to be one of the largest amounts of area underneath that curve there. So all I got to do is find 1. So let's see what happens. Let's do math. Let's do option number 9. And let's integrate from 13 to 15 our function, which again, we can hit VARS, that button just to the left of clear. Go to the second column for the y variables, option 1 for function, and option 1 for our function y1 that we typed in. We hit dx, and well, right there, 431.931. So this is equal to 431.931, which is greater than 400. So yes, on t equals 13 to 15, this integral C to D is greater than 400. And, we'll just say this, right? The number of cars turning left is more than 400. End of story. 1 point here for just figuring out that we needed to have more than 400 cars. 1 point for some valid interval. It didn't have to be 13 to 15. Just anything that worked, anything that was more than 400 would be acceptable. 1 value for actually finding a value that was more than, showing that there was a value that was more than 400, and 1 for the answer with the explanation. And that's the end of this rate FRQ, which was question number 2 from the 2006 AP Calculus AB exam. All right, this is question number 4 from the 2006 Form B AP Calculus AB exam. This is a rate FRQ here. And so what we're given to start off with is a rate in calories per minute at which a person that's using an exercise machine burns calories, and it's modeled by the function f. Our f of t is negative 1/4 t cubed plus 3/2 t squared plus 1. And for 0 to 4, and then from 4 to 24, it's piecewise linear. And they've given us a graph of f up here, right? So we've got the little curved piece from 0 to 4, and then we've got the piecewise linear stuff from 4 to 24. We want to find f prime of 22, indicating units of measure. Well, f prime of 22, that's the derivative of f. In other words, it's the slope of our graph here. So in order to find that slope, we just do the average rate of change between the 2 points. And so we can do 3 minus 15 over 24 minus 20. 3 minus 15 is, of course, negative 12. And 24 minus 20 is 4. So we get negative 3. And it wants us to indicate our units. So the graph was in calories per minute. But if we take a derivative with respect to time, we're getting calories per minute squared. And so you just get 1 point there in part A for finding the value with the correct units. In part B, we want to know when is f increasing at its greatest rate. Okay? And so in order to figure out when f is increasing at its greatest rate, we need to take a look at all the times when f is increasing. So first off, we'll note that f is increasing on 0 to 4, and also from 12 to 16. Now, from 12 to 16, its rate of increase is pretty obvious, right? The rate of increase on 12 to 16 is just the slope of that piecewise linear. So just the slope of that. So that'll be 15 minus 9, right? So we'll say up here for 12 to 16, we'll say f prime is equal to 15 minus 9 over 16 minus 12, just those 2 points there, which is 6 over 4, or 3/2. So we know that from 12 to 16, it's 3/2. That's easy. On 0 to 4, though, we want to know if when that is increasing at a maximum, when it's increasing at its greatest rate. So what we're going to do is we've already got f, and so to figure out when its rate is increasing at its maximum, we need to find f prime first of all and look for the maximum of f prime. So f prime of t is going to be negative 3/4 t squared plus 3t. And then in order to find our second derivative, right, to find the maximum, right, we'll just do the power rule again. The derivative of negative 3/4 t squared should be negative 3/2 t plus 3. And so to figure out when we're at a maximum, we need to set this equal to 0. So negative 3/2 t plus 3 equal to 0. And if you solve that, you end up getting t equals 2, right? Subtract 3 and then multiply by 2 and divide by negative 3 just gives you t equals 2. And so that's when we're going to have a maximum or a minimum potentially on this interval. It's the only possibility. But we know it's a maximum because if we do a sign chart here, right, if we put on 0, 2, and 4, and we plug in something like 1 into our second derivative here, we get negative 3/2 plus 3, which is positive. So we know that f prime is increasing. And if we plug in something like 3, we get a negative. So we know f is decreasing. And so we'll say that the max occurs, max on 0 to 4 occurs at, and in fact, we'll say the max rate occurs at t equals 2 because f double prime of t greater than 0 on 0 to 2 and f double prime of t is less than 0 on 2 to 4. But we still have to figure out what that rate is at t equals 2 and compare it to the rate we got of 3/2 earlier. So at 2, we'll just find what f prime is at 2. F prime of 2 is equal to negative 3/4 of 2 squared, so negative 3/4 of 4, plus 3 times 2. Well, that's negative 3 plus 6, which is 3. And 3 is greater than 3/2, so it is increasing. We'll say this here. F is increasing at its greatest rate at t equals 2. And we got 4 points for this. One was for finding the value of f prime here on 0 to 4. So 1 point there for just getting f prime. 1 point for showing that f prime had a max at t equals 2. 1 point for showing that the value of f prime on 12 to 16 here was less than our value, so really saying 3 is greater than 3/2, and 1 point for the answer that it must have been t equals 2. In part C, we want to find the total number of calories burned over the time interval 6 to 18. So in order to find that, all we really need to do to find the number of calories burned, if we have the rate, is just integrate the rate. So we're going to integrate f of t dt from 6 to 18. And that's part of our piecewise linear portion of it. So really we can just use some geometry here to figure out what these areas are. So from 6 to 12, it's just a rectangle. From 6 to 12 is 6 units, and it's got a height of 9. So we'll do 6 times 9 to begin with. Then we're going to add to it, we'll say the part from 12 to 16, because that's a trapezoid. So to find the area of a trapezoid, we do the base, which is 4, or not the base, but the height, which is 4. And then we multiply that by the average of the bases, which are 9 and 15, because we're going up to 9 and up to 15 here. So 9 plus 15 over 2 times the 4. Then we'll do this rectangle, which is 4 by 15. So, well, how far are we going? We're going to 18. So actually, we're not going to go all the way to 20. We're just going to go to 18 here. So that'll be 16 to 18 is 2, and then times the height of 15. And so now we just need to figure out what this is. We get 54 plus well, 9 and 15 is 24, and 24 times, 24 divided by 2 is 12, times 4 is 48. And then we'll add to that 30, and looks like 54 plus 48 is 102, plus 30 more is going to be 132 calories in total burnt on that interval. And we got 2 points for this question here. 1 for just using the appropriate method with an integral in the areas, and 1 for actually doing it correctly and getting the answer. In part D here, it says the setting on the machine is now changed so that a person burns f of t plus c calories per minute. And we want to find, for this setting, find c so that an average of 15 calories per minute is burned on 6 to 18. Well, the average amount burned from 6 to 18 ought to be 1 over 18 to minus 6 times the integral from 6 to 18 of the function that represents the rate at which the calories are burned, which is now f of t plus c dt. Right? This is just the mean value theorem for integrals, right? The mean value theorem for integrals says if you want the average of something, then we do 1 over b minus a times the integral from a to b. And we want this average to equal 15. So we need to just figure out what this is equal to here, what this value for c is. So 1 over 12 here, if we multiply 12 times 15, that's going to give us, what does that give us? That gives us 180, right? So we're going to end up with the integral of f of t plus c. Well, really, I mean, we can just kind of go in because we already knew, we don't have to actually do that. We already knew that the integral of f of t was 132 on that interval. So let's just bring that over first and separate this. So the integral from 6 to 18 of f of t dt plus the integral from 6 to 18 of c dt needs to equal that 15 times 12, which we just said was 180. And then we already knew also that the integral from 6 to 18 of f of t, this was equal to 132. So if I subtract that over here, 180 minus 132 is going to be 48. So what we've now got is that the integral from 6 to 18 of c, which is in fact just c times t evaluated from 6 to 18, needs to equal, looks like it was, what did we say it was, 48? And 180 minus our 132 was 48. And so we end up trying to figure out what our c value here needs to be. So what we've got is 18 c minus 6c is equal to 48, or 12c is equal to 48, or c is equal to 4. And that's worth 2 points. 1 for the correct setup here with the mean value theorem, and 1 for the final answer. And that is the end here of this rate FRQ, which was question number 4 from the 2006 Form B AP Calculus AB exam. All right, this is question number 2 from the 2007 AP Calculus AB exam. It's a rate FRQ where we have some water in a storage tank that is modeled by a continuous function. And we got rates at which the water enters the tank and rates at which the water leaves the tank. So f of t is the rate at which it enters, and g of t is the rate at which it leaves the tank. And we have a graph of both f and g. It tells us the intersection points, which is nice. And And it also tells us that at the beginning, at t equals 0, we have 5,000 gallons in the tank, right? We have an initial condition. So part A just says how many gallons of water enter the tank on the interval from 0 to 7. Well, the amount that enters the tank is just the rate at which it enters integrated. So the rate at which it enters is f of t. So all we want to do is do an integral on the interval from 0 to 7 of f of t dt. You don't want to include the initial condition. It doesn't say how much is in the tank, right? It doesn't care about how much leaves the tank. It's just about how much is entering on that time interval. So we're just going to use our graphing calculator here to do the integral by hitting math and option number 9, FNINT, from 0 to 7 of that f of t function, which was 100 t squared, so we'll use x squared, times the sine of the square root of x dx. And it tells us 8,263.8. So if we round that to the nearest gallon, which is what it asked us to do this time, it should be 8,264 gallons. And of course, we get 2 points here, 1 for the integral setup and 1 for the final answer. In part B, it says find the time intervals during which the amount of water in the tank is decreasing and give a reason for each answer. Well, the amount of water in the tank should be decreasing. Write this out. The amount of water in the tank decreases when the rate at which it's leaving is greater than the rate at which it's entering. So it decreases if g of t is greater than f of t. So that's when the amount of water in the tank is going to decrease, right? If the rate at which it's leaving is greater than the rate at which it is entering into the tank. And so g of t is this piecewise linear function, and f of t is the curve that we've got on there. So it sure looks like, according to our graph, this is happening on, well, the line is above the curve here from 0 to that first intersection point, which it gives us as 1.617. So we'll say this happens on 0 to 1.617. And again, later on, right, looks like from 1.617 till 3, the curve is above the line. But starting again at 3, right here at 3, non-inclusive of the 3, of course, we are above the curve here with the line until we get to this other intersection point of 5.076. So, and this actually should be a parenthesis here because they're equal to each other at the 1.617. So we'll say, and from 5.076, from 3 to 5.076, right? That's 5.076 is where that stops happening. So, and 3 to 5.076. And that's really sufficient. It wants the integrals as one point and a reason is the other point. So the reason is g of t is greater than f of t on those intervals. In part C, we want to know at what time is the amount of water in the tank the greatest. So we're looking for the maximum of a function representing the amount of water in the tank. So let's write a function to represent the amount of water in the tank. The amount of water in the tank should equal the initial amount plus the integral from 0 to whatever time we're looking at of the rate at which it enters minus the integral from 0 to t of the rate at which it leaves. So this should tell us the amount of water in the tank at any given time. And so if we want to know when is this function at a maximum, we want to find the derivative. A prime of t which should just be f of t minus g of t. Right? Because the derivative of 5,000 is 0, and the derivative of an integral from a constant to a variable is just of a function is just the function. So that applies for both the f of x and the g of x. So now we want to know, when does this equal 0? When does f of t minus g of t equal 0? Or in other words, when does f of t minus g of t, when does f of t equal g of t? And so we know when that happens, f of t equals g of t they equal each other here at the 1.617 and the 5.076 values. But we also have to take into account what's going on at the endpoints, right? Like, so at t equals 0, it could be a possibility, and at t equals 7, it could be a possibility. And also, we need to think about what's going on at t equals 3, where g of t kind of has this jump in it, right? Because the derivative there is going to be undefined at 3, because g doesn't exist at 3, right? Or the derivative of g doesn't exist at 3. So what we really need is, in other words, we need f of t minus g of t to go from a positive value to a negative value, right? If f of t minus g of t is the rate of change, when that rate of change goes from positive to negative, then that tells us that we're potentially at a maximum. And so instead of having an equals here, I'm going to say, when is f of t minus g of t greater than 0? When does it switch signs? So in other words, like, when does it switch from f of t being greater than g of t to the opposite of that? And so f of t changes, like f of t, we change here at 3, right? F of t is greater than g of t as we approach 3, but then afterwards it's not. And at 7, f of t is greater than g of t. And of course, we could also check the endpoint of 0, but these places where we indicated these 1.617 and 5.076, in those cases, we're going from the amount that is draining is more than the amount that is being pumped in, to vice versa. So those are going to be minimums on our function. So what we really need to do is just test what's going on at the beginning and at 3 and at 7. And so what we'll do here is we'll just do, to find a of, we know that a of 0 is 5,000. That's what we started at. And then we want to find a of 3. So a of 3 ought to be 5,000 plus the integral from 0 to 3 of f minus however much drains out from 0 to 3, which it's draining at 250. So that'll just be minus 250 times 3. So we'll do that on our calculator. We'll do 5,000 plus the integral, math option number 9, from 0 to 3 of our function 100x squared sine of the square root of x. And then we're going to subtract from it 3 times 250, which is 750, which is going to give us 5,126.591. It's sent around to the nearest whole number, so we'll just say 5,127. So we'll say this is approximately 5,127. And then at 7, a of 7, right, is just going to be that value that we just found, right? In other words, it's going to be 5,000 plus the integral now from, but we'll just do it from 0 to 7. The integral from 0 to 7 of f of t dt. And then we have to subtract how much we lose from 0 to 3, which we already said is 3 times 250, so that's 750. We also have to subtract how much we lose from 3 to 7, which is 4 times 2,000, right? Because we're draining at a rate of 2,000 from 3 to 7. And so now we'll go back in here, and we actually already had the integral from 0 to 7, so I'm just going to grab that value. That's how much was added in from 0 to 7. And then we'll go ahead and we'll subtract, or we'll add in the initial amount of 5,000, right, since we already had that integral from 0 to 7. So now that's how much we had in plus how much was pumped in, and now we need to subtract the amount that was removed. Well, that was the 750, and it was also the 4 times 2,000, which is 8,000, which drops us down to 4513.8 or 4514. And so the maximum amount is going to be this 5,127 gallons. And our justification is going to be, we were only choosing these values, and we tested A of 3, 7, and 0 to check them, and we got this final answer here for 1 point. So 1 point was just the justification here with the conclusion. 1 point was, actually they gave you 1 point for A of 3 and 1 point for A of 7, the actual amounts at A of 3 and A of 7. 1 point just for testing 3 in general, and 1 point for having the correct things in our integrals, so f of t's. And so that is all of the points there for part C. And that is the end of this rate FRQ, which was number 2 from the 2007 AP Calculus AB exam. All right, this is question number 3 from the 2008 AP Calculus AB exam. It's a rate FRQ, and we've got oil that's leaking from a pipeline, lovely, on the surface of a lake, and it's forming an oil slick, and the volume is increasing at a constant rate of 2,000 cubic centimeters per minute. It takes the form of a right circular cylinder, both radius and height changing with respect to time, volume, of course, being the volume of the cylinder, pi r squared h. And the first question is, at the instant when the radius of this oil slick is 100 centimeters and the height is half a centimeter, the radius is increasing at 2.5 centimeters per minute. What is the rate of change of the height of this oil slick with respect to time? Well, we know that, we have this equation v equals pi r squared h, so dv dt should equal the derivative of that. So that's a product rule derivative. It's going to be pi r squared times the derivative of h with respect to t, plus the derivative of the pi r squared part, 2 pi r dr dt times h. So we know that dv dt is constant at 2,000. We know that at the time we're interested in, the radius is 100, so we've got 100 squared here. We've got a dh dt. That's what we're looking for, right? How fast is the height changing? We've got 2 pi. We've got an r here, again, of 100. We're given dr dt, that the radius is increasing at 2.5, so that's a positive 2.5. And our h is just 0.5 as given in the problem. So all we have to do is just solve this for dh dt. So this is a calculator question. So first of all, we're going to do, we're going to do our 2 pi times 100, and then times a 2.5 and times a 0.5. That's all of the stuff that was included right here. So we're going to do 2,000 minus that. So we'll just hit 2,000 minus second and the negative sign, uses your previous answer. And then we need to divide by pi times 100 squared. So we'll say dh dt is equal to, we'll just divide this. We'll just hit divide because it uses your previous answer. and then it's pi times 100 squared. You can just type out 10,000 if you want, but you can also just do that in case you're afraid you're going to make an arithmetic error, and we get 0.039, and this is going to be in units of centimeters per minute. And so for part A there, you got 4 points. We're doing this kind of a related rate question here. Well, not kind of, it is. 1 for noting that dv dt was 2,000. 1, and for noting that dr dt was 2.5. And then you also got 2 for this expression for dv dt, so correctly taking that derivative using implicit differentiation and the product rule, and then 1 for your final answer. Part B says we have a recovery device that arrives on the scene and starts removing the oil. And the rate at which the oil is removed is 400 root T cubic centimeters per minute. Oil continues to leak at this rate of 2,000 cubic centimeters. We want to find the time when the oil slick reaches its maximum volume. Well, the maximum volume is going to occur when the rate at which the oil is leaking out finally hits the same rate as the oil is being removed from this lake, right? And so effectively, we just want to know when is the rate of change of the volume going to equal 0. So the rate of change of the volume, which we could say dv dt, is 2,000 minus the rate at which it's being removed. So in other words, when does this equal 0? Well, that'll be when r of t is equal to 2,000, right? Or we could just graph 2,000 minus r of t and see when that is equal to 0. And so we'll, and we don't even have to really do the graphing of it. Like we can just, this was a calculator problem, but this is a pretty straightforward function to solve, right? 2,000 minus r of t just means that, if we added the 400 over here like we just had a second ago, we'd have 2,000 equals 400 root t, or divide 2,000 by 400, 5 equals root t, so t is going to be 25 minutes. No real need here to use your calculator to figure that out. And we know that that's the possible time here when this happens. And what we want to do is we want to make a little statement here because it says to justify your answer. We know that dv dt is greater than 2,000. Or not, well, not greater than 2,000, but it's greater than 0, right? The rate of change of the volume is positive on 0 to 25. And we know that dv dt is less than 0 on 25 to infinity, right? Basically, we don't really need an infinity there. We could just say t, maybe better to just say t greater than 25, since we don't know when all of the oil is being removed once it's all finally removed. And so that tells us that the max is at 25 minutes. And so a little statement that tells us that the rate was positive, then the rate was negative, and therefore the amount was at a max when it changed from a positive rate to a negative rate. And you got 3 points for that. 1 for the setting r of t equal to 2,000. 1, or just 2,000 minus r of t equal to 0 would work. 1 for the answer and 1 for the justification. All right, here in part C, it says by the time the recovery device began removing the oil, 60,000 cubic centimeters of oil had already leaked. We want to write, but we don't have to evaluate, an expression involving an integral that gives the volume of oil at that maximum time of 25. Well, if we already had 60,000, we're going to have to do 60,000 plus something here that tells us how much we had at 25. Well, in order to find out how much you have at 25, you have to integrate the rate at which that volume is changing. Well, the rate at which that volume was changing was 2,000 minus r of t, right? You always integrate a rate to get the actual amount. So this is the rate at which the volume changes. So we're going to integrate that on the interval that we care about here, which is from 0 to 25 minutes, because it continues to leak from t equals 0 out until that 25-minute time period when it's at its maximum. So that is our expression. That is the total amount that we have. They gave you 2 points for this, 1 for having the initial condition and the right limits from 0 to 25, and 1 for the integrand being correct. And that is all 9 points here on this rate FRQ, question number 3 from the 2008 AP Calculus AB exam. All right, this is question number 2 from the 2008 Form B AP Calculus AB exam. This one's a little bit different than some of the other ones, but it's most in line with a rate FRQ, so I'm calling it a rate FRQ. And we've got for t greater than or equal to 0, r of t, this 120 times 1 minus e to the negative 10t squared function, represents the speed or rate in kilometers per hour at which a car travels along a straight road. The number of liters of gasoline used by this car to travel x kilometers is modeled by g of x, that other function, in terms of x. And we want to know how many kilometers does the car travel during the first 2 hours. Well, if we have its speed, we can integrate the speed. So this is kind of like a motion type question here for this part of it. And we can integrate that speed from 0 to 2. So we'll integrate r of t dt from 0 to 2. And this is a calculator question, so we'll just use our calculator to find this value. So we'll hit math, and option number 9, we'll do the integral from 0 to 2 of that function 120 times 1 minus e to the negative 10 t squared. We'll use x, so negative 10x squared. We'll close that parenthesis and put in our dx and get 206.370 kilometers. Right, so we're integrating this rate here to get the actual amount. And we got 2 points there for this, 1 for the integral setup and 1 for the answer. In part B, it says find the rate of change with respect to time of the number of liters of gasoline used by the car when t equals 2 hours. So we're looking for the rate of change of the number of liters of gas used. Well, the number of liters of gas used is g of x. So we are looking for dg dt. We want the derivative of this with respect to t. Well, the derivative of a function g of x with respect to t should be the derivative of that function with respect to x times the derivative of x with respect to t. Right? That's the chain rule that we're using here for implicit differentiation. And we'll note that this dx dt value that we're getting here, well, that's the rate of change of the kilometers with respect to time. So that's just our speed, right? This is just equal to r of t. It's the rate of change of the kilometers with respect to time. So what we need to do here is we need to figure out, we're looking for dg dt at 2. So dg dt at t equals 2 should be dg dx, right? When t is 2, well, when t is equal to 2, we should be able to figure out, we already figured out in part A that the number of kilometers, right, at t equals 2 was 206.370. And then we're going to multiply that by dx dt at 2, which is just r of t at 2, which is just r of 2. And so we'll go ahead and figure out what that is. using our calculator. So we're going to go in and we're going to first take the derivative, math, option 8. We're going to take the derivative of g with respect to x at that 206.370 value. So the function g was 0.05x times 1 minus e to the negative x over 2. And we want to evaluate that at 206.370. And then we're going to multiply that by r evaluated at 2. Well, multiplying that by r evaluated at 2 is multiplying it by 120 times that 1 minus e to the negative 10t squared. So if t is 2, negative 10t squared is going to be negative 40. So we're doing 0.05 times 120 times 1 minus e to the negative 40, which comes out to be exactly 6. So our answer here is dg dt at t equals 2 is 6. And our units here, because it says indicate units of measure, right? Well, g was in liters, so it's 6 liters. And then we took the derivative with respect to time, which was in hours, so it's 6 liters per hour. You got 3 points here. 2 points just for using the chain rule, right? For getting dg dt equals dg dx times dx dt. And then 1 point more for the final answer. In part C, it says how many liters of gas have been used by the car when it reaches 80 kilometers per hour, right? So basically when r of t equals 80, right? So let's first see when r of t equals 80. And the easiest way to do that is to just graph r of t, or even to graph r of t minus 80 and see when that is equal to 0. So we'll graph r of t minus 80 and see when that equals 0. So we'll hit y equals, and we'll do our function r of t, which was 120 times 1 minus, again, e to the negative 10t, or x in our case, squared. Now we're going to subtract 80 from it, and we're looking for when it hits that the t-axis, or the x-axis here, on the interval from 0 to 2. So I'm going to hit window up here in the top left and change my x minimum and my x maximum to 0 and 2, so that that's all I'm looking at on my graph. And now we can see when that equals 0 is when the car first hit 80 kilometers an hour. We'll hit second trace, pick option 2 for 0, and we'll have to scroll over a bit to the left here till we can see our cursor, because it started at x equals 1. There it is. Now we're to the left of that x-intercept. We'll hit enter. We'll go to the right of that x-intercept and hit enter. And we can see that that happens at 0.3314532. So we'll go back here and we'll note that this happens at t equals what did we just say? We just said 0.3314532. So that's the time when it actually hits 80 kilometers per hour. And we want to know how many liters of gasoline we've used by then. So in order to figure that out, we need to be able to plug that t value in here into g of x, but we can't do that, right? Because this is the number of liters of gasoline used to travel x kilometers. So what we need to do is we need to figure out how many kilometers this car has gone. And so to figure out how many kilometers the car has gone, we're going to have to integrate the rate function, again, that speed function. So we're going to integrate from 0 to 0.3314532, our r of t function. That's going to tell us the the number of kilometers it's traveled, and then once we have that value, that's our x that we can plug into g of x to find our final answer. So we're going to do math on our calculator. We're going to go out of there. We're going to hit math by hitting second quit. Math, option number 9 again. And we're going to integrate from 0 to 0.331453. Once again, that r of t function, which is 120, times 1 minus e to the negative 10x squared dx. We get that it's traveled 10.7940959 kilometers. So this is 10.7940959 kilometers. And so now what we need to do here at the end is we need to figure out what g of that value is, right? Because that's our x. That's x. So we're going to now find g of 10.7940959, which means we're going to just plug it into our g of x function up there. So we'll go back to our calculator. We're going to do 0.05 times this value. We can just go up and hit enter on that if we want, or we can just do second answer. Our second, the negative sign gives us answer, uses the previous answer. So that's the first part of it. And then it's times 1 minus, and then it's e to the negative x over 2. I like to do a little fraction here, so negative x, which is our previous answer. So I'm just going to hit second answer this time, divided by 2. We'll close out those parentheses, even though it should evaluate it correctly without doing that. And we end up getting 0.537, and this is liters of gasoline. 0.537 liters is our final answer. You got 4 points for this. 1 for setting r of t equal to 80. We got 2 points for doing this distance integral correctly, and then 1 point for plugging that distance into g to find our final answer. And that is the end of this rate FRQ, sort of like a combination of a motion and a rate, but more a rate FRQ. Question number 2 from the 2008 Form B AP Calculus AB exam. All right, this is question number 2 from the 2009 AP Calculus AB exam. It's a rate FRQ. We're given a rate at which people enter an auditorium for a rock concert, and it's modeled by that function r of t. From t equals 0 to t equals 2, it's measured in people per hour. And we know that when the doors open, no one is there, and 2 hours later, the doors close and the concert begins. We want to know how many people are in the auditorium when the concert begins. Well, we just have to integrate from 0 to 2 the function r of t, right? You integrate the rate to get the amount. Now, this is an integral that could really easily be done by hand, but because this is a calculator question, I suggest you just use your calculator to do the integral so that you don't make an arithmetic error. We're going to hit math, and option number 9 down here. Again, you can just hit the 9. You don't have to scroll down to it. We'll just integrate from 0 to 2, and then we're going to put in our function, which is 1,380t squared, so we'll use x squared, minus 675, in our case, x cubed, dx, and we'll get 980. So I suggest you use the calculator just to make sure you don't make an arithmetic error. So, and you could always check it by hand if you wanted to. But we got 980 people, 2 points for that, 1 for the integral, and 1 for the answer. In part B, we're looking for the time when the rate at which people enter the auditorium is at a maximum. So we want the rate to be at a maximum, which means we want to find r prime and see when r prime is equal to 0. Well, r prime, if we take the derivative of r, 2 times 1380 is what? 2760. So we're going to have 2760t. And then 3 times 675 is 2025. So 2025t squared. And of course, we can, we can factor out the t from this if we want to. We just end up with t times 2760 minus 2025t. When we set that equal to 0, and you can do that on your calculator if you want to set that equal to 0. But we just end up getting t equals 0, which is one of our endpoints, and we end up getting t is equal to 2,760 divided by 2,025. I'm just going to use my calculator here to see what that comes out to be. 1.36296. We'll just call it 1.36296. Just to approximate here. 1.36296. And then, of course, we also would want to check at the other endpoint, which is 2. And so now we just want to evaluate what's r of 0, what's r of 1.36296, and what's r of 2 to see which one is the largest. R of 0 we can see, I think, pretty easily is 0. So now we'll just use our calculator to evaluate the other two. So we need to do, our r function was 1380 times t squared. So we can always just use our previous answer by hitting second answer instead of retyping it. So answer squared. And then minus 675 times that previous answer cubed. And so that tells us 854.527. And then, of course, we'll do it with 2. And so if we're doing this at 2, it's 1380 times 2 squared, so times 4. And then we'll subtract from that 675 times 2 cubed, which is 8. And we get 120 for r of 2. So we can see that the rate is at a maximum at, so we'll say max rate at t equals 1.36296 hours. And you got 3 points for that. 1 for just considering r prime equal to 0, 1 for getting this interior critical point, and 1 for saying that's the answer with some justification. Your justification is you tested the 3 possibilities. In part C, it tells us that we have a total wait time for all the people in the auditorium. We add up the time each person waits, starting at the time the person enters and ending when the concert actually begins. So we have now the function w, which models the total wait time for all the people, and its derivative is 2 minus t times r of t. We want to find w of 2 minus w of 1, right, which is going to be the total wait time for those who enter the auditorium after t equals 1. Well, the w of 2 minus w of 1 should just equal the integral of w prime of t dt from 1 to 2, right? That's equal to w of 2 minus w of 1, because the integral of w prime is w, and you evaluate the upper limit and the lower limit and find the difference. So all we want to do is evaluate this integral, which we can do just using our calculator. So we're going to hit math, option number 9 again. and we're going to integrate from 1 to 2 of this w prime function, which is 2 minus t, and again, we're using 2 minus x, and then times the function, which was 1380x squared minus 675x cubed. And so that is what we're asked to integrate, 2 minus t times r of t from 1 to 2, and it comes out to be 387.5, in this case, hours. So the total wait time of all the people that entered between 1 and 2 hours was 387.5 hours. And you got 2 points for that, one for the knowing this integral was what we needed to do, and one for the answer for actually doing the integral correctly on your calculator. And in part D, it asks us to find out on average how long a person waits for the concert to begin. And so we're going to consider all people who enter the auditorium after the doors open. So what we need is the entire wait time, right? So basically that's what is W of 2. Right? We want to know what's the entire wait time of everybody that entered all the way up to 2. And then we want to divide that by the number of people that actually went to this concert. Well, the number of people that went to the concert we found in part A, that was 980. So we're looking for W of 2 divided by 980. And so in order to find W of 2, we have to do an integral here, right? And so what we're going to do is we're going to do an integral from 0 to 2 of W prime of t dt, and then divide it by 980. Because we know that at 0, right, the total wait time at 0 was just 0. So what we can do here is we can note that this is just 1 over 9, it's the same as 1 over 980 times W of 2 minus W of 0. Well, at hour 0, nobody had waited at all. That's equal to 0, right? This part right here is equal to 0. So really all we're looking for is this, right? And this integral here, we could just do on our calculator. So we'll put our alpha x here to put our nice little fraction out in front. 1 over 980, we'll do math. We'll do option number 9. We'll integrate from 0 to 2, and we'll do it of our W prime function, which is, once again, same thing we just used a minute ago, 2 minus x and 1380x squared minus 675x to the third. Put your dx there, and it looks like we get 0.776 hours if we round. So the average person waited 0.776 hours, about 3/4 of an hour, a little over 45 minutes there. And you got 2 points there, 1 for the correct integral and 1 for the final answer. And that is the end of this rate FRQ, question number 2 from the 2009 AP Calculus AB exam. All right, this is question number 1 from the 2009 Form B of the AP Calculus AB exam. This is a rate FRQ. We are given the radius, capital R of t, of a cross-section of a tree that has circular cross-sections. We're saying it's growing at a rate modeled by the function dr dt is 1/16 of 3 plus sine of t squared centimeters per year for 0 to 3. And we know that at t equals 0, the radius is 6. And we're going to denote here that our area of the cross-section is A of t. And so the first thing it asks us here is just to write an expression with an integral to find the radius at any value between 0 and 3. So we know that it starts out at 6. So our initial condition is going to be 6. So r of t should equal 6 plus an integral, in other words, a amount that it changes by, right, from 0 to t of this function, 1/16 of 3 plus the sine of, we'll call it x squared dx. Right? And so we have the 6, which is our initial condition, and then our dr dt expression is what we're integrating to get the amount that the change in this radius is, right? Since dr dt is the rate at which it changes, its integral should be the amount it's changed. And we'll just add the 6 to it. And then it says use your expression to find r of 3. So r of 3 should be 6 plus the integral from 0 to 3 of 1/16 of 3 plus the sine of x squared dx. And so we'll just use our calculator, since this is a calculator question, to figure out that value. We'll do 6 plus math, option number 9. And again, you can just hit the 9. You don't have to scroll down to it. And it's an integral from 0 to 3 of 1/16. I like to do alpha and then the x button to give me a nice little fraction there, 1/16. And then it's 1/16 times 3 plus the sine of x squared. And we've closed, I think we've closed all of our parentheses now with one more. And we'll put our dx on the outside. And we end up with 6.611 when we round. And that's our radius. And of course, we could put units on it if we want to. We don't need to, but the radius is measured in centimeters. So we'll call it centimeters. And 3 points there for part A. 1 for the for having the right integral. 1 for the full expression for r of t with the 6 plus, and 1 for our final answer. In part B, it wants us to find the rate at which the cross-sectional area is increasing at t equals 3. Well, the cross-sectional area, the area is going to be pi times the radius squared, and the radius is represented by r of t. So we have the area is pi times the radius squared, since this is a circular cross-section. And if we want to find the rate at which that area is increasing at t equals 3, we need its derivative. Right? So a prime of t should be pi times the derivative of 2r of t squared, which will be 2r of t. But then the chain rule says you have to multiply by the derivative of r, which will be r prime of t. So that's our expression for a prime. If we want a prime of 3, that should be pi times 2 times r of 3 times r prime of 3. And we've got r of 3, right? We found r of 3 just a minute ago in the previous question, right? 6.611, that's r of 3. And r prime of 3 will just be the value of dr dt at 3. So we can use our calculator to do this. So part of what we're multiplying is the 6.610 number. So we'll just say that times 2 times pi. So that takes care of the pi, the 2, and the r of 3. And now we just need to multiply by r prime of 3, or this value here, at 3. So we'll now do times 1/16. Right, so we can, well, really we can just do divided by 16 there, times 1/16. And now we're going to multiply that by 3 plus the sine of 3 squared, and that would be the sine of 9. And that gives us 8.858 when we round. And we've got our units on it, just like it asked, indicate units of measure. we got 1 point for the expression for a of t, we got 1 point for the expression for a prime of t, and we got 1 point for the correct answer with the appropriate units. In part C here, we're going to evaluate the integral from 0 to 3 of a prime of t dt. Well, that should just be the integral from 0 to 3 of a prime of t dt should just equal a of 3 minus a of 0. And we just found a of 3, and so now we just need to also put in a of 0 there. So a of 3 was, well, actually we found a prime of 3. So we just need to do a of 3, right, where a of 3 was our pi times r of 3 squared minus pi times r of 0 squared. And so r of 3 we found in part 1. R of 0, our radius at 0 is 6. So this is just going to be minus 36 pi here. And this will be pi times our r of 3 value squared. We'll put that into our calculator. Our r of 3 value was this, 6.6108. So we'll do that squared times pi, and then we'll subtract 36 pi from that, and looks like that gives us 24.201. And this is area in centimeters, so it's centimeters squared. And it asks us to interpret the meaning of this. Well, this is how much the cross-sectional area, how much this area of the cross-sections is growing from 0 to 3, right? If a prime is the rate of change of the cross-section, then this integral is the amount it changes. So we'll write, and this is the amount the cross-sectional area changes from t equals 0 to 3. And that is the end of this question. We got 3 points for that. 1 point for using the fundamental theorem of calculus here, 1 point for the value that we got, and 1 point for our explanation. And that's the end of this rate FRQ, question number 1 from the 2009 Form B AP Calculus AB exam. All right, this is question number 2 from the 2009 Form B AP Calculus AB exam. This is another rate FRQ. We've got a storm that's washed away sand from a beach, and the edge of the water is now getting closer to a nearby road. So the rate at which the distance between the road and the edge of the water was changing during the storm is modeled by this function f of t, root t plus cosine t minus 3 meters per hour. And the edge of the water was 35 meters from the road when the storm began. And we know the storm lasted for 5 hours, so we'll say from t equals 0 to t equals 5. We're also given the derivative of this function, f of t, which was the rate. So the derivative of the rate is 1 over 2 root t minus sine t. We want to know what was the distance between the road and the edge of the water at the end of the storm. Well, in order to do that, we just have to take our initial condition, 35, right, the initial amount that the storm was away from the edge of the, or that the water was from the road, and add to it the rate at which the distance between them is changing, integral. Right, so we're going to integrate from 0 to 5 our function f of t dt. And so since this is a calculator question, we can just go right ahead and do this on our calculator. 35 plus the integral, math, option number 9, We're going to integrate from 0 to 5 of f of t, which was the square root of t, or we'll use square root of x, plus cosine x minus 3. And of course, we'll throw a dx on there at the end, giving us 26.495 meters when we round it. And for part A there, you got 2 points, one for the integral and one for the correct answer. In part B, it says, using correct units, interpret the value f prime of 4 equals 1.007 in terms of the distance between the road and the edge of the water. So if the derivative at 4 is positive, that means that the distance between the road and the edge of the water is increasing at this rate, right? Since its derivative is positive. So we'll say that something like 4 hours into the storm, we'll say 4 hours into the storm, the rate at which the edge of the water is approaching the road here is increasing at 1.007, and our units here are going to be, this was in meters per hour, so this will be meters per hour since it's a derivative, or meters per hour squared. And so we got 1 point for the interpretation and 1 point for meters per hour squared. In part C, it says, at what time during the 5 hours of the storm was the distance between the road and the edge of the water decreasing most rapidly? So when is the distance between them decreasing the fastest? So the rate of decrease, or the rate of change of it, is f. So we are looking at when do we have a minimum or a maximum. Here is what we're kind of looking at, right? Of our value of f, right? So we're looking for decreasing most rapidly. Well, that's going to be a minimum, right? So what we're going to do here is we're going to take f prime of t and set it equal to 0, because that's when we can have a minimum or a maximum. And we'll just use our graphing calculator to do that. So we'll go y equals, and f prime was 1 over 2 root t, so I'll hit alpha x to just give me a nice fraction here. 1 over 2 square root of x, and then we had minus the sine of x. And we want to know between t equals 0 and t equals 5, when does that equal 0? So we'll hit window and change our x minimum to 0 and our x maximum to 5. And we'll hit graph, and then we can see that there are 2 different places where this equals 0. So we'll hit second, trace, option 2 for 0. And we'll see that as we scroll over here, a ways, quite a ways, and hit enter once we're to the left, and then scroll to the right and hit enter once we're to the right, and hit enter a third time, we get 0.6618655. So 0.6618655 is one option. So this is t equals 0.66. It was 6618655. I forgot what it was. 655. And the other one we can find here. We'll do the same thing. Second trace. We'll choose option 2 for 0. We'll scroll over here to the right till we're close to that x-intercept. We'll hit enter. We'll scroll all the way to the right of that x-intercept. We'll hit enter. We'll hit enter a third time, and we'll get 2.8403832. So we got 2.8403832. And of course, we also know that the closed interval here that we're talking about from 0 to 5, we could have also had our value at a minimum at 0 and at 5. And so we're going to just evaluate f of 0, f of, and I'm going to just call this a and this b just to make life easy so I don't have to rewrite those numbers. F of a, f of b, and f of 5. All right? So we'll just use our calculator to do that. Now, f of 0 we should be able to do really easily without the calculator. The square root of 0 is 0. The cosine of 0 is 1, and 1 minus 3 is -2. So that's easy enough. But for the other ones, we'll need to use our calculator. So we've got the first one was at 0.66, etc. So we'll do the square root of that value, 0.6618655, plus the cosine of that value, 0.6618655. And then we'll subtract 3 from it and get negative 1.398 if we round. And then we'll do that for b. So we'll do the square root of our value of b, which was 2.8. What do we have? We had 2.8403832. And we want to add to that the cosine of 2.8403832, and then subtract 3. That gives us negative 2.270 when we round that. So we'll give that a negative 2.270. And then we'll do the same thing for 5. So we'll go in here and we'll do a square root of 5 plus the cosine of 5, and then minus 3, and that is negative 0.480. And so now we can see that the decrease the most rapidly, so the minimum here is at f of b. So it is decreasing most rapidly at t equals b, or t equals 2.8403832. And they gave you 3 points for this. 1 for just considering f prime of 0, 1 for finding the correct answer, and 1 for the justification and that you tested those values. And of course, we also could have looked here at our graph of the derivative, right? And we could have seen that we had to have a maximum at 0.66 because the derivative was positive all over here to the left of 0.66. And then it was negative, so we had to be decreasing. So we're going to have a minimum when we go from decreasing, a negative derivative, to increasing, a positive derivative. So we could see that the minimum could have only occurred at 0 and at this value that we found that it did occur at of 2.840. So you could have done it that way as well, and only tested a couple of those values, right? You could have only tested 0 and f of b, but then you'd have to write a statement about the signs of the derivative as well. All right, here in part D, we've got a machine that's now pumping sand back onto the beach so that the distance between the road and the edge is growing now at g of p meters per day. P is the number of days since the pumping began, we want to write an equation involving an integral, which if we solved it would give the number of days that sand must be pumped to restore the original distance between the road and the edge of the water. So we want the amount that the road changed to equal the amount that they pump back in. So we know that it changed by an integral of 0 to 5 of f of t dt. But when we pump, we're going to be pumping positive amount back in, so we have to cancel this out with a negative here. And we want this to equal an integral from, well, whenever we start pumping, right? So whenever we start pumping is, well, p is the number of days since the pumping began. So we're going to do this in terms of p. We'll integrate from 0 to some number of days, g of p dp, right? So we're just going to say, okay, we're pumping at this rate, so we need the amount that we pump from 0 to some x value to equal the amount that it changed from 0 to 5 during the storm, right? And the opposite of how much it changed, because it was, we're pumping more sand back in to increase this, so we have to cancel out the negative. Or in other words, we could also bring this over here and just say the amount pumped minus the amount lost is equal to 0, right? Either way would be fine. But regardless, whichever way you choose to do it, you got 2 points, one for having an integral of g here, and one for the whole thing as an answer. And that is the end of this rate FRQ, question number 2 from the 2009 Form B AP Calculus AB exam.